Mechanical Engineering, NIT Warangal. He is having 21 years of experience in teaching and research. His research interests are
the general natural examples are we need to understand the nature or our body or anything. So we can correlate our manufacturing system also with these things, right? So okay, these are all just normal scientific definitions. So that is the activities whose environmental impact is below the level that the self recovery capability of the natural environment can deal with. So there is a level, so below that if you use any resources, again it will be regained, okay. But if you use above that level, the regaining or recovery capability is not possible. That is what we have to use below that level. And then the design of human and industrial systems to ensure that the same thing, whatever you are designing, any manufacturing systems or anything, then we have to check this whether we are using the level above that recovery level or below that recovery level. So if you are using below the recovery level, then we are not harming our environment, right? So that is what we need to understand this one. So what is sustainable development? The same thing, whatever we are manufacturing, it may be some car or any refrigerator, or you take any product, we use so many resources, right? We use raw material and we use machines and we use electrical energy and we use some oils, right? Some cutting tools or cutting fluids, etc. So we can use so many things to get the product from a raw material. So in between, from raw material to product, there are so many steps are there, right? Maybe we are using our energy, right, and electrical energy and also raw material, etc., etc., whatever required. So during this cycle, what we have to develop is whatever we are using the resources, we should minimize. That means we have to use in such a way that the recovery level should not cross our utility. That is what the basic understanding of sustainability and sustainable development. So maybe you can see this one so that you can understand what is going on nowadays. So this is what initially our earth or nature. So like this, we are using natural resources and we are making our products, our requirements, but there are so many negative effects in the nature. So I think you understand. So we are using our environment, right? Like plants or water.
Any question for back side print?
Of resources in the recent years, like these are the statistics, some of the statistics. So we are consuming more resources than all the previous history in the last 50 years, and also we are using six-fold in the metal production, and oil consumption 8-fold, and natural gas consumption 14-fold after the 2005, or between the 1950 to 2005. Even after 2005 also the usage is still increasing. And similarly 60 billion tons of resources are now extracted annually. This is what 50% more than the 30 years before the status, right. So that is what before 1950 whatever resources are utilized. So and now whatever we are using is almost increasing 3 times, 5 times, 6 times, depends on the resources. So if we are going on like this, what is happening? That is, carbon emissions are increasing, right. So we need to understand here we need to understand this one, like this is what the CO2 total emissions by countries. So like that the China is emitting more emissions, right, and then USA, and then India, Russia, Japan, like this. These are the different statistics in 2010, 2014 and 2015. Of course in now in 2024 or 23 it is still increasing. So this is what the total emissions of CO2 gas, and this is what CO2 per capita, that means per head how much amount of CO2, I mean how much amount of resources we are using, and from that one how much amount of CO2 is releasing. So before going that we need to understand a small thing. All of us know we cannot create energy or we cannot destroy energy, right. So only thing is we are converting one form of energy into other form. So that is what we are doing. So whatever the natural resources available, maybe trees or maybe animals or maybe resources from the earth, like mines or etc., or water, etc. So all these things we are converting into our required product form. So for this conversion we required some machines, right, and we required electrical energy, and we required some other oils, etc., etc. So how we are getting this? For example, all of you know how we are getting electrical energy. So there are 3-4 types of resources, like maybe we are using coal or water or maybe from the sun rays, etc. So if you are getting from the coal, for example we are taking energy from the coal, so we are burning the coal and then we are converting the natural resources of coal into electrical energy. But that is also again during this burning process there are lot of gases are coming out. So all these gases we can call it as greenhouse gases. I will discuss later, but all these gases or all these emissions whatever coming out, we convert in the form of CO2 emissions, right. There are calculations, equivalents are there. So, to quantify how much amount of energy we are using or how much amount of natural resources we are utilizing, normally what we can do is whatever the thing that we are converting into CO2, right. For example, if I ask you what is your property value, so you may have some house and land and then some gold and some cars, etc., etc. Finally, what we can say, you are having worth of some 1 crore or 5 crore or 10 crore or 100 crore, like that. So, that means what we are doing, this land value we are converting into rupees and the house value we are converting into rupees and the gold value we are converting into rupees, like that. Similarly, here also whatever all the emissions we are delivering to the environment, that will be converted into CO2 emissions. There are calculations, right. So, from that one, the total emissions to the environment we calculate in terms of CO2. But actually we are not delivering only CO2, we are delivering so many other gases also, but we are converting into equivalent to CO2 because for our calculation or for our quantity purpose, like how we are converting our assets into money, right, that is the same thing. So, this is what the CO2 total emissions by country, and this is per capita, and this is what the population growth. So, why these CO2 emissions are increasing? Obviously, the population is increasing and our requirements are increasing. So, we are utilizing more amount of resources in a shorter period of time, so that this total natural resources are converting into other products or other forms. So, during this one there are so many wastages are there, or so much of energy consumption is there, and then whatever the total thing is converting into CO2 emissions. So, that is what the CO2 emissions are increasing and the pollution is increasing, and whatever this one is also increasing, right. So, this is what the atmospheric CO2 concentration as a function of time. So, whenever in the olden days in 1000, 1100 etc., like this, so the rate is like this, but when it comes to 2000, right, it is drastically increasing. Okay. So, this is what the percentage of carbon dioxide in the environment. So, obviously, when it is more than what we can able to sustain, obviously the temperature rise is there in the atmosphere, and also we get the health problems and everything. So, we can call it as the pollution or whatever, right. So, what are the reasons for this one? Only reason is we are converting the natural resources into the useful products, right. But you know, there is a after usage what we are doing, we are not recycling everything, right. So, we come back to that point. So, these are 10 hottest years globally. So, year by year the temperature rise is there. So, the temperature rise is like this. So, from 2007 to 2016. So, of course, again 2016 to 2024 it is still increasing, right. So, then now we go back to our sustainable manufacturing. So, till now what we discussed is the general thing, right. So, just to understand what is sustainability or how we are utilizing the our natural resources for our requirements, etc. So, maybe different examples, right. So, but the thing is we need to understand what is happening. So, now we concentrate only on the manufacturing sector. So, then This is what actually the manufacturing is. So, now this one is the consumption of today's rate. So, this is what we are using nowadays, but actually this may be the blue line is maybe the consumption with the increasing efficiency of the manufacturing process, or maybe whatever all the things, but still actually we need to reach this level, that is required consumption rate to reach sustainability is this one, and this is the actually sustainability rate. We discussed in the starting, there is some level, below that only the replenishment is possible, recovery is possible in the natural resources, above that recovery is not possible, right. So, similarly this is the one, the cutoff point. So, if our usage is up to this line or below that line, then there is no damage to the environment. Okay. So, it will be recycled or it will be replenished, but nowadays we are going like this. There is lot of gap between the sustainability line and our actual usage line. This is what I am talking about, the natural resources. Okay, right. So, now this is what actually all countries are expecting. That is why we are all talking about sustainability and technologies for sustainability, or maybe measures to take the sustainable things in any of the sector, but I do not know when we will reach it. So, but just we are talking about numbers, but how to achieve it, right. So, we cannot stop eating, right, and we cannot stop using our mobile phones or our cars, anything, right. So, still we are increasing the usage, but how can we reach this level when the population is increasing, usage is increasing, but we are aim is to decrease the usage of natural resources, but how it is possible, right. So, that is what the main aspect here, we need to understand the sustainability aspects in the manufacturing process, so that we can able to minimize the usage of these natural resources. So, then the same thing. So, here we can able to increase, this is sustainability framework for reference. So, we cannot reach suddenly from this line to this line, right. So, step by step we have to increase the efficiency of our process, like whatever the manufacturing of this one, or maybe reusing or recycling everything, and also the consumption rate also should be decreased, and finally we may reach the sustainable rate if we try, or if we understand the nature, and if we understand the if we follow the nature's requirements, like our body requirements, right. So, our body and nature are almost same. Okay. So, for example, you are working for 3 hours or 4 hours, etc., right, without eating, or maybe you are working 1 day or 2 days, then you can able to recover after eating some food or something. But if you work 1 month or 2 months like that without required food or something, then what will happen? Definitely will become weak, or some damage will be there. Similarly, the nature also same. So, if you utilize the resources and if you give sufficient time to recovery, then normally it will come to the normal level, like any of the trees or water levels or natural resources what we are getting from the mines, etc. But if you do not give that time and you are completely using and also at higher levels, the recovery rate is also less. So, that is what main reason for this global warming and pollution, etc., etc. So, then how can you achieve these things? That is what first thing is we have to reduce the utilization of the resources, right? So how can you reduce utilization of the resources? Yeah, that is what reduce means, less usage only, but this is, there are so many things. So even in your daily life we are using so many things, like we are using cloths, so we are utilizing some raw material, and we are utilizing some resources to run the machines and power, etc., etc. So, and also we are watching our mobile phone. So to manufacture that mobile phone, again some resources are required, right? And everything, we are using these bags, our laptops, and everything, whatever we are using, we are increasing the utilization, but we are not reducing the utilization. So here the first point is we have to reduce the utilization of the natural resources. So that is what, for example, you take the power generation, right? So if you use maybe wind power or water power instead of the thermal power plants, or instead of the usage of oils, I mean petrol based fuels to generate the power, then what will happen? We can able to reduce, right? So we can use solar energy or wind energy or hydraulic source, but nowadays we are not utilizing up to the maximum level. We are still utilizing the thermal power. Of course, compared to the previous last 20 years or 30 years, now the power generation from the solar energy or maybe from the hydraulic power is increased. But at the same time, if it is increasing 10%, our utilization is increasing 20% because of the population growth, as well as the number of products what we are getting, and also like this. So I will give you a small example. Normally what we can do, we buy our mobile phone, but many of us, we don't use till it is obsolete. After 1 year or 2 years, whenever the performance is less, or whenever the new mobile phone is coming to the market, we are buying that one. So you are throwing it, right? Am I right? Or maybe you can sell for something, but finally it is there, somewhere it is there. So all these electronic goods, like previously we used CDs, so that material is not biodegradable, right? And maybe we are using hard disk, laptops, everything. All these also we are not utilizing till the end of its life, right? We are changing the products, depends on our requirements, or sometimes depends on our passion or whatever, so many reasons. So what is happening? This product is obsolete. Like TV is also same. We are changing whenever the new product is coming, right? So same, our clothes also same, chappal, shoes, everything. Nowadays we are not utilizing the total lifetime of the product. So here we need to reduce the usage. I just told you few examples, but I am talking about manufacturing point of view. So reduce means not only reducing the product use, right? And we have to reduce the everything, usage of water, usage of power, or anything, usage of any of the natural resources. I am not saying you don't use mobile phone or you don't use any of the product, but you can use your resources maybe up to the maximum efficiency, right? So that is what the reduce, and then reuse, right? So maybe you can reuse some of the products like your clothes or maybe any of the products, right? So like water bottles. So many products maybe we can reuse, but now this reuse technology is also developing, but in our country it is very less. So that is what reuse. And then recycle. Maybe you cannot reuse the product in the same form, so we can recycle the product and again make the raw material with that one and then go for the another product, like that. So if you are able to follow these three rules, right, then maybe you can able to reduce that consumption rate, or maybe you can able to attain this sustainable rate. So it is very difficult actually. Everyone is saying we can reach by 2050 or 2080, like that, some of the countries, but it is not possible. It is just we are aiming, right? We don't know how we can reach it. So then this is what recycling and remanufacturing. So if you follow all these things in each and every product, whatever possible, then we can able to reduce the usage of natural resources and maybe we can able to attain the sustainable rate. And then already I told you previously, CO2 footprint. So that is what we need to understand. Whatever we are utilizing the natural resources, that one is converting into CO2 emissions. Already I told you, everything we convert into CO2 emissions, but actually it is not CO2 emissions, but like our assets, how you are converting, like that, whatever emissions or whatever the damage to the nature, that we are converting into CO2 emissions and we calculate in that form. So that is what is this carbon footprint is the total amount of greenhouse gases produced directly or indirectly, and to support human activities, that is what human activities, whatever we required, maybe water bottles or maybe our mobile phones or pens or books or shoes or clothes, etc. See, everything we have to get from some of the natural resources. So we have raw material, we have a product, in between it is a process, right? So that process is again utilizing so many machines, manpower, and some maybe chemicals or maybe oils or maybe so many things, right? So that is what each and every step we are utilizing the natural resources and we are converting one form of energy into other form. So that is what whatever we are utilizing, that is usually expressed in equivalent tons of the carbon dioxide, right? So when you drive a car, this is one example, the engine burns fuel which creates a certain amount of CO2. So it creates not only CO2, other gases also, but for our purpose, calculation purpose, we are converting everything into CO2 with some multiplication factor. So then, so depending on its fuel consumption and the driving distance. So similarly, when you heat your house with oil or gas or coal, then also generate the CO2. That is what we are using heaters, we are using ACs, right, or we are using geysers, okay, or we are using our tube lights, everything. So everything is again converting some natural resource into our required energy thing. So that is what in every process some greenhouse emissions are there, right, or heat generation is there. So that is what we convert into CO2 footprint. So even if you heat or cool your house with electricity, that is the generation of the electrical power may also emitted a certain amount of CO2. That means either directly or indirectly we are utilizing the natural resources only. So I have one question, okay. So we are all working, right? So for example, I am working, so I am getting some salary per 1 month, maybe 1 lakh rupees. What I am doing with that money? anyone, not only me. So we are taking that money and we are purchasing whatever we require, right? So it may be rice, or it may be vegetables, or it may be our daily requirements. So again this amount is going to different people. So I am purchasing vegetables. So that vegetable market person getting money, not only from me, like so many people. Again what he is doing this money? Again he will buy whatever his requirement. So that money is again going to different people, maybe for the farmer. So what he is doing? Again he will buy some other items, right? Maybe fertilizers, maybe seeds for his cultivation, and again for household life. So like this, if you think or if you see, just this money is transferring one person to other person, right? But finally what? Finally what? Nothing. So finally this money is again just transferring to one person to other person. Maybe like few people are accumulating, right? Accumulating in the form of just a digital or whatever. So again the currency will not be with him. Only on paper I am having some 100 crores, you are having some 200 crores, or someone is having only 1 crore, like that. So but finally whatever we are doing is, we are eating the food, we are drinking the water, and we are using the same thing for our daily purpose. Whether you are getting 2 lakhs rupees, I am getting 1 lakh rupees, and some other person getting 50,000, whatever, finally everyone is doing the same thing, right? But maybe I can buy a shirt with 1000 rupees, he will buy a shirt with 500 rupees, and someone buy a shirt with 2000 rupees, or I can use a car with 10 lakhs and someone use car with 1 crore, like. See, finally this is what only the difference of our satisfaction or our ego or whatever. I am using a branded car, I am wearing a branded shirt, or I am having a big house. But whatever the big house, you are sleeping on the same area, right? See, like this, if you think really everyone utilizing the same natural resources like water, air and food. All other things are just conversion of these things into different forms. That's it. But finally we require the same amount of oxygen to live, more or less, same amount of water to drink, and same amount of food to eat. This is what our final requirements. But still we run to earn more, right? Am I right? So I am not saying you don't work and you don't earn, just try to understand the nature. Okay, so that is what I am saying. You can live with maybe 10,000 rupees per month also, 50,000 rupees per month also, or 50 lakhs per month also. Only difference is the level of satisfaction, that you can satisfy with 10,000 also, you can satisfy with 10. Of course, the society or whatever the system is pushing us to earn and spend money, right? Because otherwise what will happen? If you don't want money, then we don't work. Am I right? That is what happening nowadays. The government is giving some free, so many people don't work. So if you don't work, then there is no productivity, right? So If you don't work, just eating and sleeping, what will happen? The system will be damaged. That may be environment, that may be your body. So actually the energy required for our body is same, the natural resources required for body is same, whether it may be a poor person or it may be a rich person. But only thing is, by creating this level of satisfaction or system, etc., etc., we are pushing the people to work, right? So the same thing happening here, but in this system we are forgetting what is actually required, and we are spending more, and we are spoiling the environment or something. So here what is happening is, something is required, definitely something is required, but once we started running, we don't know where to stop. So after reaching the level of required also, we still try for the more. It may be money, or it may be product development, or it may be process development, or it may be creating new product or innovations or whatever, right? Am I right? So maybe 50 years back, or hardly 30 years back, we don't have cell phones, or maybe in the 50 years back we don't have internet, but still people are happy at the time also. And maybe before that we don't have even telephone, and we don't have any electricity, but at that time also people are survived. Now also the society is running, people are surviving, but what is the difference? So I don't know whether we can call it as development, or so we are developing at the same time we are damaging in them, right? So the balance is required, right? So that means we don't say don't create new product or don't manufacture, etc. Because if you don't manufacture, then what will happen? You don't start a new company. If you don't start new company, then you don't require any machinery, you don't require any electrical energy, you don't require any workers, but the population is increasing. How to get money for them? They have to work. That means you have to create the work, right? So this is all happening just to create the work to the people. Every development or everything is happening just to create the work to the people. Because if there is no work, if they don't work, then again damage to the environment and their body. So this is because of everything happening with increasing the population. But shall we stop the population? It is also not possible, right? This is a natural process, right? So like that depends on the some of the things are naturally happening, and those things are forcing us to develop a new product or to develop a new process or to go for the new things, and again those new products or process or requirements are forcing us to use the natural resources. So all this is a system, right? Life cycle. But here what is happening is during this life cycle we are missing, and we are using what more resources than what is required. Okay. So nowadays because of that one we are facing some natural disasters, right? Like temperature rise is there, global warming is there. Because of that one some health issues are there, like that, some problem for the cultivation, etc., etc. So many things are there. So here we need to understand this carbon footprint. So that is your carbon footprint is the sum of all the emissions of CO2 which were induced by your activities in a given time frame. That is what I told you. Whatever we are using, that one we can convert into this CO2 emissions, right. So then what is this carbon footprint, or how can we determine is the actual gases we produce each day by driving or heating or cooling our homes or using electricity, etc. So I am just quoting few examples, but all the activities require some energy. So items we use also affect our carbon footprint. For example, the carbon was produced in the making of your clothes, and carbon will be produced as they are breaking down after you throw them away, or the more we buy, the more emissions are produced, right. So because of these things, the carbon footprint is increasing in the environment. So this is what, when we are using the vehicle, then the emissions are more, then carbon footprint is increasing. Then maybe you are cutting the nail, then also carbon footprint is increasing. And then like this, the carbon dioxide is also called greenhouse gas, causing the global warming. Already I told you, we can call it as all the emissions or whatever outputs we are getting from the process or manufacturing is called as the greenhouse gases. So over greenhouse gases which might be emitted as a result of your activities, or like example methane or ozone or some other any of the gases like nitrogen, etc. And these greenhouse gases are also normally taken into account for the carbon footprint. That means we have a multiplication factor, this much amount of nitrogen is releasing and this is equivalent to this much amount of CO2 gas, like that we convert, right. And they are converted into the amount of CO2 that would cause the same effects on global warming. So that is called as the equivalent CO2 amount, that is represented by the CO2e. So all the emissions or all the wastage what we are giving to the environment is converted into finally CO2e. That is what we are calculating the CO2 emissions. So these are the general greenhouse gases like water vapor and carbon dioxide, methane, nitrous oxide, ozone, and these perfluorocarbons and hydrofluorocarbons and sulfur hexafluoride, etc. Like this, there are so many things, so many gases are there which we don't required and harmful to our environment, right. But these are all there emitting into the environment or mixing with the air. So which reducing the oxygen levels in the environment. So again this is danger to the humans or maybe animals or maybe marine, this one, that is more amount of more amount of this wastage is delivered into the sea, then the marine life is damaging, right, we don't get fishes, etc. So these greenhouse gases can be measured by recording emissions at source by continuous emissions monitoring or by estimating the amount emitted by multiplying activity data. This is what I told you, right. So we are converting this into by multiplying this one, and then these conversion factors allow activity data, that is to be converted into kilograms of carbon dioxide equivalent. So finally we are converting everything into CO2e. So this is CO2e is the universal unit of measurement that allows the global warming potential of different greenhouse gases. Like how we are telling what is the property you have, or what is the value of your property, or what is the income of certain country, or what is the overall per capita of certain country, how we are telling, right, like that everything and also you know, if you go any country or anything, even per capita income is represented in the USD, right. That means all countries they converting their this one into USD and telling their level of income or whatever. And similarly, that is the normally universal or worldwide the currency what we are everyone accepting. Similarly, we are representing our own properties in the form of money, rupees, right. So here also same, all the environmental emissions we convert into CO2 equivalent and we tell what is the emission size in the form of CO2, right. Are you understanding? So this is what the life cycle. So then we have the raw material. So first we can extract the raw material from the mines. It may be whatever, coal or iron or whatever it may be. We extract the water, and also we extract the material from the trees, right. These are all the natural resources, okay. And then we design and we produce a product, okay. That means we design how to manufacture this shirt, right, or how to manufacture this pen. We design first what raw materials are required and what machine we have to use and what process we have to follow, like. Then from this one, whatever you understand now, then you take one product, right. For example, you have to manufacture one car tire, or you take machining itself, because our topic is machine shop. So you can tell me one product which we can manufacture in the machine shop. Maybe we can manufacture piston rings, right. So piston rings required some metal, maybe aluminum, right. So first we have to extract the aluminum from the mines, maybe in the natural form or maybe in the any other form. Then we have to prepare the aluminum alloy, what we required for the piston rings manufacturing. So we get raw material, then this raw material comes to your machine shop. So this machine shop contains again lathe machines or milling machines or drilling machines or cutting machines, etc. Then or forming, etc. So we convert first this raw material into required form, maybe like a tube or maybe like a rod or maybe like a rectangular piece, etc. We convert into billets, etc. Whatever required, depends on the product. Then we use the lathe machine or drilling machine or any other machine, and we convert the raw material into required shape and size. So one process may not be, or one operation may not be sufficient, then we can go for secondary operation, maybe we can go for grinding or drilling or some other finishing process, and finally we are producing a piston ring, and that one we are using in the maybe IC engine. That IC engine we are using in again maybe two-wheeler or four-wheeler or maybe aeroplane or rocket or etc. So how many steps are there from getting raw material here to the usage of car? There are so many steps, okay. Of course here we are just showing the main steps, that is design and product, and then packing and distribution, and then use and maintenance. Suppose you take a car, a small part in the car, there are so many steps, right, or otherwise you are using a brakes. So the brake system itself contains so many individual components, brake shoes, right, or pedal or whatever. So again that brake shoe is required or manufactured nowadays by some composite material. So this composite material contains maybe aluminum alloy and maybe some silicon carbide particles reinforcements or something else. So first we have to get this silicon carbide and we have to get aluminum, and then we have to prepare or we have to manufacture a composite. Then for this one we require some other equipment, maybe stir casting or some other equipment. Then we manufacture, and then that one again we cut into required shape. For that one we require some machine or lathe machine or laser cutting machine or any machine. So in the machine shop itself, once the raw material is coming and the product is going out, so we are utilizing so many machines, so many cutting tools, and we are utilizing the oils and grease and all these things for the machines, and also we are manufacturing the cutting tools separately and machine separately, and again bringing to the machine shop. We are utilizing lathe machine, but that lathe machine also manufactured by some other company, again by using the cast iron or steel, right, and again that manufacturing unit required the raw material from the mine, and again electrical energy, and to manufacture that one again so required some other machine, individual components are required, then we can assemble. So we require bolt and nuts, Am I right? So you take a simple bolt and nut or piston ring or like that to get the final product, right? So we are utilizing all these steps. So first we are designing, depends on our requirement, depends on the functionality, and then we are producing, and then we are packing and distribution to the customer, and the customer is utilizing, and then coming to here, sometimes we are dumping, right? And sometimes this is what the disposal or reuse and recycling. So if we are completely disposing, then we are not utilizing, or the environment or resources are wasting. So here we need to understand the reuse and recycling, but in this step we need to understand the reduce. So in the design stage itself, in the manufacturing stage itself, we have to reduce the usage of the raw materials, or usage of the electricity, or usage of the cutting tools, or usage of the cutting fluid, or usage of the oils, whatever. So don't waste energy, or don't waste raw materials, or don't waste any of the natural resources. So in each step, if you follow the sustainability aspects, maybe we can able to reduce and reuse and recycle. So each and every step. So then this is what maybe the cloths we are using. So the cultivation of cotton, this is the life cycle of the cloth. So cultivation of the cotton in country A, and then I will show you the total thing. So process at the spinning and weaving mill in some country, you can take it as a country or place or city, whatever, and then we are manufacturing a product in some other city or country C, and then we are going for the marketing and sales in the country D, then used by the consumers, then waste collection. Then sometimes we can go for collection by the second hand shop for reuse, and then or otherwise it is going for dumping and recycling, and then going to the nature. So some of the products, even if you throw out to the nature, then no issue, it will be recycled or reusable after a period of time, right? So but some of the products we cannot reuse. So that is what we use the word, either the item is biodegradable or not. So if paper is there, if throw out and it will mix with the soil, maybe after a period of time it is biodegradable, or any of the leaves, it is biodegradable, right? But if you throw your pen drive or your laptop or your hard disk, it is not biodegradable. After 10 years or 20 years or whatever the period, after 100 years also that will be like that only. So this is what we need to understand in the life cycle of any product. That is whatever we are showing here, the same thing here. So we have a raw material. So to get this raw material, we are using fertilizers, energy and water, because we are manufacturing the raw material for the cloth is maybe a cotton or silk or something, whatever the material. So that we are again cultivating, right? So for this cultivation we required fertilizers, and we required energy, and we required water. So here also again we are using the natural resources. So this fertilizer again manufacturing by some other natural resources, and this energy is produced by some other natural resources, and water is directly we are using from the nature. So like this here what we are doing is the raw material itself here utilizing some other natural resources, and then the process, again for processing of this one we are using energy, and we are using cloners and dyes, etc., that is to get the required colors and designs, etc., right? And then manufacturing, that is after getting the cloth, maybe converting into this shape, size, or some design something. And then packing, for packing we are using papers, plastics, and again some waste will be there. And then transport, for transporting we are utilizing vehicles or rails or whatever, that is also energy is there. So use, then for usage again we are washing our clothes daily, right? For that one we are utilizing the bleach, detergents, or again water, right? So after usage of certain period, sometimes we can reuse, or sometimes we can dispose, or sometimes we can recycle. Of course we are not doing, but at least recycle process is available, or technologies are available, or if the recycle companies are available, then maybe you can give it to that one, right? So I think you can see recycling machines of nowadays, at least water bottles, at least these cool drink tins, bottles, and maybe some metal parts from the cars or bikes. So they are recycling. May not be in our country, but many of the countries they are already recycling. But even though they are recycling, that level of recycling is not what we are using, right? So like that, what is happening is we are in each stage we are using natural resources, right? But this usage is very high nowadays, so that we are not able to manage these sustainability aspects. So you just think in the same way, right? So in the machine shop, whatever products we are manufacturing. So in the machine shop normally we use lathe machines, drilling, milling, etc., etc. That means naturally our raw material is a metal, right? So we manufacture so many parts, bolt and nuts, or some screws, or some washers, from small part to very large part, like two-wheelers or four-wheelers. Of course directly the four-wheeler we are not manufacturing, but individual components manufacturing and assembling and using. So that is what machine shop is important for each and every product, right? So the same thing, maybe in the other form. Here we are getting the raw material acquisition for any product. Previous one is maybe for shirt, and this is for any product. Raw material acquisition is there, then we utilize the energy, we have emissions and wastage. So this is all input and this is all the output. So in each stage we have emissions and we have wastage of energy, right? So then finally we have waste and emissions, okay. So then this is what life cycle assessment of any product, that is we have a raw materials extraction, processing, impact on the environment, design for sustainability, economic, social and legislative issues, and use of sustainable materials, materials for green energy, end of the life issues, that is recycling, etc. So in each stage we need to understand the sustainability aspects. That is what I told you in the starting itself. Even if we say I don't use any product, I don't start any new innovation, I don't start any factory, means that is also problem, right? Because the population is increasing, everyone want to eat, so they want money, they want food, then so this is a cyclic process, right? So but we cannot stop the process, but we have to run the process in a proper manner, or so that is what in each process we need to understand what is the impact on the environment, and here we have to design the product for sustainability. Same thing, whenever you are designing a product, we have to keep these points in mind, that is reduce. So we have to minimize the usage of raw material, usage of energy, and usage of the resources, and then uh, reuse and recycle. So in such a way, if you design a product, then at up to certain level we can able to attain the sustainability. And then this one, that is economic, social and legislative issues. At the same time, in the design stage, we need to consider the economic, social and legislative issues. That means whatever I told you, some of the things are there. If the government says, I don't give salary and you don't pay taxes, then it will not work out, right? So they will increase salary, they will increase taxes. It is a recycling process. So same thing, the government rules are there, same thing the private companies also following, etc., etc. Am I right? So for example, one company is giving more salary to you means definitely they will expect the same thing, right? Maybe not in terms of only number of hours working or maybe something else, but in other way the company should get more than that from you, otherwise how can they get the profits, right? So same thing, that is what we need to understand in the process. And then use of sustainable materials, that is what instead of non biodegradable materials, if you use biodegradable materials, maybe at least it is possible to reuse or recycle that one. So that is the materials for green energy, this is also same. And then end of the life issues, that is recycling and reuse is required. So if you design our total process and product in such a way that whatever we are using, whatever we are manufacturing is by the concept of reduce, reuse and recycle, then at least we try to reduce the carbon emissions and also we can able to attain the level of sustainability. And the same thing again maybe in another way. So if you take the environment, there are so many ways which are impacting, that is materials, energy, air pollution, water pollution, wastage, resource depletion or toxicity or biodiversity or acidification, ozone depletion, global. So all these are there, all these are the concerns to the environment. Why environment is required? To live the human beings or any animals, again environment is the main thing, right? So if the temperatures are increasing, if there is no rain, if there is no water, if the plants are not growing, then what will happen? Again, why we are doing, the basic object itself is damaging. Why we are developing all these products? If you live, then you can use this product. But if you don't have water, if you don't have oxygen, if you don't have food to eat, then why all these laptops, cars, all these things? Waste, right? So that is what we have to balance everything. So then here at the same time the social responsibilities are there, that is equal opportunities, that is we have to create work for each and every one, and then the stakeholder involvement and customer satisfaction, wages and benefits and education, health and safety, employment, etc. So to take care of all these things, again development is required. So then the economic, so we have the sales and profits, investment, shareholder value, contribution to GDP, value added, all these things, right? So any of the entrepreneur, they don't start company, right, to give salaries to the workers. Am I right? Why they start company? Definitely they want to earn something for the profits. So if they get the profit, then they run the company. If they run the company, the product will be there, then so many people will get employment and they will get salary and again they will get money. So this is a cyclic process. So if we have a benefit, then only we do anything. But the benefit may be in other ways. So, the entrepreneur benefit is different, the employee and benefit is different, right? Like that everyone is selfish and some benefit is required, not only in terms of money, right, in some other way, right. So, then so all these things if you confine to only manufacturing, right, but everything is linked. So, we can say the manufacturing systems though create material wealth for humans and they consume a great amount of resources while generating lot of waste. That is what we discussed till now. We are developing many products, but at the same time we are consuming more amount of resources and creating many waste and causing for global warming. And then the waste generated during the manufacturing process during the use of products and after the end of the life of the products is responsible for degradation of the environment. That is what we discussed till now. So, then this is also we discussed the concept of reduce, reuse and recycle. So, this is reduce concept is at the item of energy or material consumption and socio-economic impacts throughout the product's life cycle. So, from design stage to the disposal stage we have to keep this in mind, and then reuse, that is design the product for disassembly. So, parts can be reused, and the recycle, that is select material that can be recycled. Okay. So, like this we follow this 3R sustainability, that is reuse, reduce, reduce, reuse and recycle, then maybe we can able to achieve up to certain levels. Then if you go beyond that, there are other things, 6R philosophy, that is along with reduce, reuse and rethink, then maybe we can go for recycle, then we can go for rethink, and also we can repair and replace. So, while designing itself we can rethink, either you can use any other material, or we can use any other machine, or we can use any other process, or maybe we can use any other shape, etc., so that we can able to get that one. And then every time do not throw away if the product is not working, you think of repair, right, and then replace, that is we can replace some of the materials or some of the products or some of the process to reduce the CO2 footprint or emissions, etc. Maybe we can make the alternatives, right. So, I will give you small example on this one in the machine shop, right. That is what if you see in olden days we are using or we used to manufacture any of the machining process with the help of cutting fluids, you know, the conventional cutting fluids. If you see in your lab or workshop, we use a white fluid, right, all of you know what is that? It is a natural cutting fluid. It is nothing but mix of some oil plus water, but do you know water and oil cannot mix. So, to mix this oil into water we use some chemical that is called as surfactant. But why we required water and oil in a coolant or cutting fluid? Any one of you? See, in any machining process heat will be generated, like all of you studied chip formation, right. So, there we have primary deformation zone, secondary deformation zone or tertiary deformation zone. So, heat will be produced, right. In the lathe machine also, if you are doing simple turning operation, immediately after completing turning operation, if you touch the workpiece or tool, it is very heat. So, that means we understand the heat is producing in the machining process, right. So, this heat is producing because of so many reasons. One is friction between the tool and workpiece, and one is to cut the material we are using some energy, that energy is again converting into heat, like that some of the reasons are there. So, to reduce the heat generation, we need to reduce the coefficient of friction, so we want lubrication. So, oil is a lubricant, but at the same time we cannot do it zero, only we can able to reduce certain level, right. So, already some amount of is generated, then we have to extract that heat from the machining zone, otherwise there is a damage to the cutting tool and workpiece if the heat is there itself. So, we want a coolant. So, water is a best coolant, right, and also oil is a better lubricant. So, we want both the properties, cooling and lubrication properties in the cutting fluid. That is why we mix oil and water, but naturally water and oil are not going to mix, that is why we use some catalyst, that is called as a surfactant, which is a chemical. So, what it will do is, normally water is nothing but all of H2O. Even if you buy a water bottle, if you store 1 month also, it will not damage. Am I right? Huh? But the same water, if you observe in the drainage, why it is damaging? I mean, it create some of the what we can call it as some infectants, right. See, in the drainage also water is there, but that water is becoming black or creating some infections or developing some germs, all these things. What is the difference? Huh? Water is water only. Why contamination is happening? That is what my question. Pardon? Okay, because of that mixing, what is happening? That is what actually H2O molecule is stable. You can store any days, it will not damage, it will not contaminate. But whenever we are mixing this surfactant like in the cutting fluid, the H2O molecule is breaking into H plus and OH minus ions to mix with oil. Then only we get the property of both cooling and lubricant. But once the H2O molecule is breaking into H plus and OH minus ions, the lifetime is reducing. It is only few hours, maybe weeks or days. After that, this H plus and OH minus ions going to react with other things and may create these contaminated things. So, in the drainage what will happen is, we are not sending only water, we are sending so many things which contain so many chemicals. So, these chemicals are going to break the water molecule into H plus and OH minus ions. That is why it is unstable in the drainages and any of the canals, etc., wherever the chemicals are sending from the factories or from our house, etc. So, then this is becoming unstable and contamination is happening, and so many mosquitoes or so many things are developing from that one, right. So, I am going to somewhere replace. So, if you replace the cutting fluid in the machine shop, then maybe you can able to reduce the CO2 emissions, right. That is just a one point in the total manufacturing process. So, like this repair. So, instead of throwing out whatever the product we are using simply outside, if you get any problem, but if you are repairing and using for a long period of time, then you can save your money as well as you can save environment also, right. So, like that we can rethink in the design stage and we can repair some of the products and also we can replace some of the materials. We can able to improve the sustainability cycle, etc., but in different stages. In the different products it is different, just we have to apply these basic things. So, this is a small example. So, this is you can see the water bottle, right, maybe they are converting into like chappals. I am not saying you use like this, just if people not able to buy chappals, they can use same thing. So, like that if you think you can create so many products from the waste and maybe you can reuse it. And this is a closed loop manufacturing, that is what all these things we know, but we have to apply for each and every product. So, that is here we have the raw material going to the material and part maker and product maker, seller, user, then again collecting. And so, we have one cycle, that is in-house maintainer. So, the same after using, if you get any problem, then maybe we can maintain in-house, right, or maybe we can recover the product center, right, and then part recovery center or material recovery, like that in different stages. If you are able to reuse, then maybe we can able to attain the sustainability, right. So, if you think your daily life, this we can observe, right, that is in-house maintenance. Some of the products, if it is damaged, we can do it in your house itself. Suppose my shirt button is damaged, what I can do? We can do in your house itself, right. Or maybe some of the things we get repair to your mobile phone, maybe you can go to the shop, you cannot repair it, you can go to the shop and you can repair it and reuse. And similarly part recovery center, that is again repair means sometimes it is repairable or sometimes we have to replace particular part, right. So, suppose your fan is repaired, suppose the capacitor is damaged, you can get new capacitor from the shop, like that. And then part recovery center, product recovery center or material recovery center, like that sometimes depends on our requirement, maybe we can change one small part or one complete component, or sometimes we have to resend it, like that in the different stages we can use of reuse, rethink, etc., then it will be better. So, this is also same actually in different stages, how we are using natural resources or how to go for manufacturing, product use and product disposal and recovery, reuse, etc. This is what only different examples of what we discussed till now, okay, right. So, this is also same, but different approaches, natural resources are different for a different products. This is also same maybe in the making of the washing machine, right. So, this sustainable manufacturing is nothing but a multidisciplinary approach in which products are manufactured using process that are environmental friendly and conservative in consuming energy and natural resources and safe for employees, consumers and society. So, if you apply 3R or 6R principles and if you change the design, process, etc., maybe we can able to attain from this one. So, this is normally we can use different names for the sustainable manufacturing, that is green engineering, green manufacture, clean manufacturing or environmental conscious manufacturing, etc., etc. So, we can use this one. And then the same thing, we have to take care of the social responsibilities and environmental responsibilities and economic responsibilities while using or while developing any of the product, then only we can able to attain the sustainability. That is what I told you, we can use 6R principle or 3R principle or 6R principle, and maybe you can use this sustainable manufacturing technique in the machine shop or any of the manufacturing unit, then we can go for this one. So, then product design and system, manufacturing information and the process, anything in each step we have to think of this one, right. So, just quickly I will show you, all these are the same concepts, but only different aspects or different products, like education research institutes, that is to do research in the new materials, to develop new process and to develop new designs, and it will go for the industry and it will go for the society and governmenting agencies. So all will work together, then only we can able to achieve the sustainable manufacturing. Okay. So then if you see the manufacturing machine shop, then normally the machine tool charter, that is vibrations or maybe cutting fluids or maybe foundry applications, all these are important in the sustainable point of view if you consider the machine shop or manufacturing. So this is what I told you already, if you use the cutting fluid, the environmental effects are there, or if you replace this cutting fluid with some other air, or maybe we can able to reduce the heat generation in machining process by any of the sustainable or eco-friendly cutting fluids, etc., then maybe we can able to reduce some of the CO2 emissions. This is also same, maybe we can use in each stage how to follow, how to check the each and every point. So this is what in the manufacturing also, like machine manufacturing or tool manufacturing or conventional cutting fluid usage or raw material development, etc., in each stage how to use the minimum energy and how to go for the sustainable material technology, all this is this one. So maybe you can replace the process, some of the process, or you can change the process steps to minimize the energy usage or maybe to minimize the CO2 emissions, etc., right. So this is what we can replace maybe the laser cutting process instead of the conventional cutting process, etc. So this is what we need to understand. So if you see here, this is the consumption of energy, and this is what the use phase consumption of energy, this is manufacturing phase consumption of energy. So sometimes we use maximum energy, but the maintenance cost is less. Like I will give you a small example. If you buy a Skoda company car, right, normally the initial cost may be more, but you need not to do servicing for each 10,000 kilometers. Okay, or all branded cars, like the initial cost is more, you need to go for servicing maybe 1 lakh kilometers or 50,000 kilometers or like that, right. Once you buy Skoda car, maybe first 3 years you need not require any maintenance, but if you buy a car of Maruti, right, you have to go for 1 month, 2 months, 3 months, then 1 year, and or otherwise 10,000 kilometers, etc. So if you compare these two products, in the Skoda, the manufacturing cost is more. Of course, whatever the cost we don't know, but we are paying more. But this maintenance cost may be less, right? But of course, that is also for year. If you consider, it may be more. Just I am giving small example. But we need not go for every 10,000 kilometers. We have to go for maybe 1 lakh kilometers, like that. But if you are able to reduce this one, that is manufacturing cost also we are able to reduce, or we reduce, and the maintenance cost also we reduce, then we reach the sustainable aspects. Or if both are high, this one is high and maintenance cost is high, that is least sustainable. Are you understanding this one? Sometimes this is high, this is less, or sometimes this is low, this is high. Sometimes both are high, that is the fourth one, and both are less, this is the sustainable one, right. Like that, if you develop the process and product, then we can attain the sustainability. So this is what in each step, if you develop machines which utilizes less energy, and if you develop process which utilizes less energy, and products which are reusable and recyclable, and then the power also, if you develop a clean power, then in each and every aspect, if you think in terms of sustainability, then we can able to develop the, or we can able to attain the sustainability aspects in the environment. The same thing, eco-friendly, cost effective, these are the things we need to understand in the sustainable machining process, okay, right. So, this is again the sustainable machining techniques. That is what I told you. Maybe we can reduce the usage of coolant, or we can change the materials, we can change the tools where we get the usage of minimum energy and minimum maintenance, right. That is what we discussed. Maybe this is in terms of machine shop, this is in terms of machining process. So, how can you understand? Actually, I just quickly close this one, maybe another 5 minutes. So, how can you understand whether your machining is sustainable or not? So, we need to understand the sustainability analysis. We have to do the sustainability analysis. That is what first we have to consider the cost. How much cost is there for starting to ending, and then we have to measure the carbon emissions, and also we have to check the eco-friendliness of the process and product, and then we need to check the biodegradability. So, if these 4 points we keep in mind, right, then we can able to attain the sustainability. So, just for a small example of maybe machining of lathe machine by using some cutting fluid and workpiece, etc. So, we can calculate like this. These are all the calculating cost, that is cutting tool lifetime. So, we are using cutting tool, what is the cost of cutting tool and how much time we are using, and machining time and speed, all these things, machining cost, energy cost. So, I think you are all studied maybe one topic, machining economics, in your BTech or MTech level. So, those things we need to apply here, but that is we study broadly, but we have to see all other points. Here we need to understand all the costs. So, find out what is the total cost of machining, and then we apply parameters to calculate the cost. So, that is what here everything we need to convert into the rupees, right. And then we have to check carbon emissions. So, this one we need to consider the electrical energy whatever we are using, and we need to consider the tool, the energy usage to manufacture the tool, and what is the energy we are using for the coolant, and what is the energy for machine, and the process, that is chip formation process. So, all these we can able to calculate individually, and by these formulas, there are formulas are there, standard formulas. So, we calculate what is the total amount energy we are considering for each and every.
Okay, I hope we are not very late. Yeah. So, the last two modules in the course that I will teach relate to surface engineering. So, I thought today I will give you a slightly broader overview of what surface engineering is, because it's a very big field, whether you believe it or not, and I hope I show you how big it is, right. And tomorrow maybe I pick one of, I was thinking I'll pick one of the technologies as an example, and then talk a little bit about that. Based on what hands went up, I think maybe I will talk more about thermal spray tomorrow, yeah, because it has changed quite a bit from the old thermal spray that people knew. Yeah, so I'll try and talk about that a little bit. What I like to do in a surface engineering course always is start with this slide. Yeah, again we are going to do BTech, MTech or postgraduate and faculty. What is common in all these slides? What do you see as a similarity in all these slides? Finishing. All right. 2 or 3 people said finishing there. Huh? Aesthetic is common. What is aesthetic about shaving blade? Hey, you are very random man. Yeah. Material usage. Everything uses material, so that's common. Huh? All right. I will say slide because everything is on that slide. Yeah. So, any faculty here? Yeah, some of you are faculty, right? Or all faculty is bunking today. Yeah. Okay. So what is common is all of these have been quoted. Yeah, all of these have been quoted for many different reasons, right? Cell phone, anti-reflective. How important do you think is anti-reflective coating? If you compare a cheap phone and an expensive phone. Yeah, how important is an anti-reflective coating on a phone screen? For your eyes, I mean, yeah, to be able to see. I for the longest time I used to carry a lousy phone, and if I went out in the sun, I don't see anything on my screen, right? If you have an expensive phone, then yeah, lots of stuff. How about this? Yeah. All of you are young guys, many of you shaving, of course. Yeah. How often do you change your shaving blade? 1 month? Couple of times in a month? Yeah, something like that. Anyone more? Oh, you're very young guys. So yeah, some of you don't use a blade at all. Yeah, but you will not believe how sophisticated a coating is used on this blade. Yeah, can anyone dare to guess what coating is used on a Gillette Mark IV blade? Stainless steel coating. Yeah, this uses diamond-like carbon with metal doping. Yeah, and that's why they last so long. I remember the old Panama blades which I used to, from third day I would struggle shaving with that. Today, 3-4 weeks you don't have to change a blade, right? Do you want a break or? Yeah, okay. Let's talk about this little bit for the ladies here. Yeah, how important is that? Yeah, what is that coating you think? Titanium nitride, correct? What does it do? It makes it long lasting, one of course. Second is it allows you to use less gold, yeah, and still retain the luster for a long time. Yeah, so there are many such examples, right? Some are obvious, some not so obvious, right? Scratch resistant, there are all these kind of coatings, right? So the point I am trying to make is coatings today are not something out of this world. You use them in everyday life, right? You go to a bathroom, open the tap. Is your tap coated? Coated? Are you sure? Your tap or tap in 5-star hotels? Or all taps are coated? All taps are coated? Are coated with what? Yeah, yeah. But you are right. All taps are coated. The only difference is by what, right? Some have a very cheap coating, maybe chrome plating or since these days chrome plating is not so popular, little bit less. If you go to a 5-star hotel, they may be coated with something close to titanium nitride, yeah, if they are of that color. So everything is coated today, right? And that's important. So as always, I will go to the definition. What is surface engineering? If you open the ASM handbook, there is a certain definition, right? Treatment of surface and near surface regions to improve properties at the surface. But I like this definition much better, right? It's a combination of component and coating materials to yield a system. There are some keywords here. System is one of them. To yield a system with properties that neither material is capable of providing on its own, right? That is crucial. Yeah, you have a bulk material, you have a material on the surface, and you are combining both of them to get very unique properties, which neither the bulk material can provide or the surface material alone can provide, right? For me, that is the best definition of surface engineering, right? Why is it crucial? Why is it necessary? I showed different things, not so important, some important. We spoke about everything from taps to artificial jewelry to razor blades, right? So why is it crucial? Because many times what you require from the bulk and what you require from the surface is entirely different, right? Let's take examples, right? If you look at bulk properties, think of any component, right? You will find that your choice of the bulk material will be dictated by these kind of things: strength, stiffness, toughness, machinability maybe, yeah, even cost, right? That's how you pick a bulk material for any application that you have, right? But if you talk about surface, then that is something completely different, right? You want surface properties which are adequate to ensure that your surface does not degrade very quickly, yeah, in whatever operation it is seeing, correct? And if you can find one single material that ticks off both of these boxes, then you are okay, no problem. But more and more, in all the examples that I showed you on that slide, you will find that you cannot find a single material that will satisfy both these properties. You will not. You cannot make the entire phone out of anti-reflective material. You will go bankrupt in one day, right? No, you cannot do that. Impossible, right? Same with razor blade. Yeah, you cannot make the entire blade of diamond like carbon. Can't do. And if you don't put diamond like carbon, then your blade wears off very quick, right? And you can extend that argument to everything that you saw on that slide, correct? So you struggle these days to find a single material that will meet both bulk and surface properties, and that is why engineering the surfaces of components is crucial, right? Crucial, and it's also very cost effective. One of the reasons for that is our ability to do research and evolve new alloys, new materials has stopped giving us the kind of returns we were getting earlier, right? Earlier you used to get property improvement as you alloyed. Now there is no more spices in the kitchen. You have used everything, right? So there's nothing more great to do by alloy development. Let's look at an example. I hope I have an example. Yeah, let's look at, since we talk about super alloys little bit in AM, how to make 718, we spoke about Haynes 282, CM247. Why did I name all these alloys, right? Because they have evolved over time. Each of them is different from the other. So if you look at olden times, right from 1940 maybe, yeah, these were all forged alloys, and you changed the chemistry to improve their temperature capability, right? And then you also went to both different chemistries as well as different processing routes. You kept doing that. But now if you see how the temperature capability has evolved, it's a pretty flat curve now. There's nothing left to use. You have used little bit of vanadium, moly, hafnium, everything that is there, you have added, right? So no more masala in the kitchen, correct? So you have to do something else if you want to improve the temperature capability, right? And that something else is a coating, right? If you compared to uncoated, if you use a thermal barrier coating, for example, you suddenly get a big rise in temperature capability, right? Depending upon what you do, yeah, and depending on what substrate you're using. Yesterday, someone was asking me about silicon carbide composites, right? We spoke about that a little bit. If you now move from nickel-based alloys to 6-SiC composites, then your need for coating is different. But again, coating is inevitable to be able to get an improvement in temperature capability, right? So I think this is important to understand. So as a summary, what can surface engineering accomplish? Yeah, what can be the reasons to engineer surfaces? Give me one reason, 2 reasons, 3 reasons. What is the reason to engineer surfaces? Most common. No. Surface finish alone is not interesting. What is the reason to engineer surfaces? Long life. Biggest reason is long life, correct. What else? Looks, aesthetics, right? Yeah, it's long life. Yeah, same. So you are right. Everyone gives me the good answer. Yeah, it's to increase life. It could also be to increase performance or provide performance that is not capable of. And third is aesthetics, looks, just to make something look good, right? So that is very important. You use surface engineering for all of these things, which, yeah, this is real life, that was just for fun. Yeah, you can use this for longer life. All these components utilize coatings. This is something that I had done 25 years ago. This is a guide vane in NHPC, nuclear hydropower, very aggressive, because where are most of our hydropower plants situated in India? General knowledge question. Yeah, where are they situated? Hill stations. Fantastic answer. Yeah, but slightly more closer than hill station. Tamil Nadu? Sorry. Yeah. Yeah. In the Himalayan region, let's broadly say Himalayan region, right? Most of these are in the Himalayan region, like Himachal and all, hill station. Yeah. And the problem there is lot of silt coming from the mountain, right? And that silt has what? It has quartz. It has a lot of alumina. It has lot of silica, and that silt wears off your guide vanes in no time, right? So we were looking at coatings to try and protect the guide vane for a long time. The problem is so severe that when your water flow is the highest, they actually shut down the plant, which is so sad, right? Because the silt will, and I was there during one of the maintenance times, right? All this is missing, it's gone. It's gone because of erosion, right? There is no shaft, there is no guide vane, nothing, right? So you need some sort of coating then to improve life. Many times performance, like thermal barrier, you need it, right? Several other things, on a camshaft, you need better properties, or a droplet erosion on a steam turbine blade. Yeah, you need something to be done on the surface so that these things live longer. This is easier to understand, right? Yeah, you just need it for good look sometimes. Many times these days, you want all three combined. Just this is not enough. You want it to look good as well, right? For instance, the shock absorbers on your motorcycles, right? It's not so hard to protect it against corrosion if you guys are driving it near a marine environment. But to do that and make it look good, That's a challenge, right? So, if you are, for example, hard anodizing, you want to give color also along with hard anodizing, right? So, uh, uh, what does that mean? If you want to put this all together, it means that your engineered surface or your ability to engineer surfaces should be also in a position to impart multifunctionality. Yeah, you should be able to get many things out of your coatings. Let's also touch upon an aspect which is easy to miss sometimes. Yeah? Why do we engineer surfaces? The two main drivers or motivation for engineering surfaces are the following, right? Many times you want the surface property as a primary function. What is underneath you don't care about, right? In the second case, which is more common, you are using a coating to extend life, right, or for protection, right? That is little more obvious. But let's look at this aspect where the bulk material is all just serving maybe as a carrier, but all the functions of that component come from what you do on the surface later on. Can anyone give me examples of that? There are many examples of this. This is easy to give. Yeah, can you give me some examples of that? Yeah, where you're looking at doing surface engineering because it imparts the function that is necessary on the surface. It's not just for protection. Can you give me examples of that? Anyone? No? Little louder, man. Yeah, that's a good example. Yeah. What else? Can anyone think of big? Hydrophobic is another example. Very good. What does it do? Excellent example. Cutting tool. Yeah. So let me tell you 2 or 3 which came immediately to my mind. Cutting tool is of course one. All sorts of machine tools where what is underneath just gives the right shape, but all of the action is because of the coating, whether it is tungsten carbide carbon, whether it is chromium nitride, titanium nitride. There are very complex coatings there. Couple of other examples, brake pad, right? You again rely on how you engineer the surface to be able to provide the properties that you need on the component surface. And this is something from our time at ARCI, where what is below just provides support and shape. Yeah, of course it should survive if you are putting it in space. It should survive the conditions in space, but the real surface property, the right kind of reflectance, etc., comes from the coating. Yeah, we used to do at that time CVD, silicon carbide, right? So that comes from the coating. The other aspect, as I said, is more obvious and easy to define. Yeah, you can talk about corrosion-resistant coatings, coatings to resist different forms of wear, coatings to protect a part from a high heat load or a high temperature. Thermal barrier coatings also fall somewhat in that category. Clearance control. How many of you know clearance control coatings? What are clearance control coatings? Anyone? No? No one has heard of clearance control coatings? Yeah. So some of you have flown before, maybe all of you have flown before. If you see the aero engine, when you're boarding, you see these fans going around, right? Yeah. Many blades, maybe 64 blades, and then there is a casing, correct? Yeah. Each of those blades is super expensive. Yeah. I mentioned yesterday that each blade costs almost as much as a Mercedes Benz. Very expensive, right? Now just imagine a situation where for some reason, these blades go a little bit eccentric and they go into the casing. Yeah, what would happen? All 64 blades would be gone, right, in no time, right? All blade tips would be gone, right? So it is common practice then to put a coating on the casing. Yeah, the purpose of the coating is to ensure the right amount of clearance between the casing and the blade tip, right? The other purpose also is, if there is this kind of incursion of the blade, the coating gives way, right? And nothing happens to the blade tip, right? The coating is what fails rather than the blade tip. So it's usually a softer coating. It's called an abradable coating. Yeah, I would also call it a sacrificial coating, right? So with that explanation, then why is this different from the other four in terms of its performance? What do you see as the big difference between this class of coatings and the other four that I show here? Can you tell? Think about it a little bit. Permanent, nothing is permanent, boss, in life, I tell you. Yeah, but I think you're there. Again, as an engineer, you need to use the right nomenclature and you need to say it in the right way, correct? So what's the difference? You're the vaguest guy, man. No.
No, like corrosion resistance and all this for the casing we use it inside, so it does not expose and it just creating a way, softer way, in this more thickness. Other thing,
All of them have predefined function. All of these, right? The biggest difference is, if I can, you have 10 more seconds till I have some water. The other four coatings have properties that are better than the bulk, right? If you are looking for a corrosion resistant coating, you are applying a material that has corrosion properties which are better than what is underneath, right? If you are looking for a wear resistant coating, again, it is supposed to be more resistant to wear than the underlying substrate, right? That's not the case here. Yeah, you actually want it to have worse properties, right? So that if the blade goes in, the coating goes off, right? In all other cases, that's not true. You want those coatings to have a far superior performance, yeah, permanent, yeah. At least that is the ambition compared to the substrate. That's important to remember. We have evolved so much in coatings now that simply saying that I want a wear resistant coating is not enough, yeah, or saying that I want a corrosion resistant coating, not okay. So if you are a designer, you have to ask more questions. If someone comes to you for a coating, you typically ask, so what form of wear? Is it abrasion? Is it erosion? Is it sliding? Is it dry sliding or lubricated sliding? Yeah. Same with corrosion, room temperature, high temperature, aqueous, gaseous, right? So because the kind of coating you pick will be different for each form of wear many times, right? So you need to know exactly what you're looking for, yeah? Just like you do when you go shopping. You must be very clear in your mind about what you want to buy, correct? Sometimes life can be tough. You may have mixed modes. You may have sliding wear and corrosion at the same time, and therefore your material would be a little bit different. Fortunately for you guys, both the processes are evolving now to be able to do that, and the materials that you can coat are also evolving. The chemistries are also evolving, so that you can get this kind of multifunctionality that is of interest, right? So we spoke about all of these things. Why surface coating? To enhance functionality in whatever form. The nice thing is today it's so versatile that you can almost tailor any property on the surface, right? So there are many ways to put on coatings, and you can make them accomplish many things, right? So that's the starting point. I would like you to remember that, yeah? some of you are BTech guys, some of you way beyond that. How many of you have at some point heard of these, right? Different surface modification technologies, electrodeposition, diffusion coatings, hardening. You have heard, all of you have heard of that in some context? Yeah? Correct? How about these? PVD, thermal spray, you have heard of these as well, right? This is how I was taught when I was doing my BTech, 1978. Yeah, I'm an old guy. In 1978, that's how I was taught. Yeah. Today, if you take a course in surface engineering, nobody will say that these are the surface modification technologies that are available for you. Yeah. Because each of these now people realize is only a family of coatings, right? Within each of these, you have many. So, electrodeposition not okay. You have to specify what else. Yeah, electroplating, electroless plating, anodizing, micro-arc oxidation, all this is electrodeposition. Same with diffusion coatings, right? You can put just about any element in, carburizing, nitriding, aluminizing, boriding, and each of them gives you fairly different properties at the surface. Same is true for the next, right? Someone is working on thermal spray, maybe they work on cold spray, but all this belongs to thermal spray today, right? So if you add all of them up, yeah, you are very happy if you are a designer because you have such a large toolbox. If you are a student, you are many times miserable because all of them are different. So if you are given a quiz later, your life is hell unless you understand what is going on. But it's nice. It's a nice time to be a designer and be able to do whatever you please at the surface, right? It's very, very powerful, right? So let's talk about these surface engineering approaches, right? They can be classified in many ways, right? There are certain approaches where you don't alter the chemical composition at the surface at all, yeah, like hardening or heat treatment. You do just some thermal treatments or mechanical working like shot peening, etc. In some cases, you change properties near the surface by altering chemistry. These are some of the examples of doing that, right? You just change, you cheat, you basically cheat, right? You make mild steel behave like stainless steel, right? By doing something at the surface, put little bit chromium and stuff like that, right? And then of course, most popular is this third category where you are actually adding an extra layer on top, which is very different from what the substrate looks like. And there are many ways to do that, as I just showed you, right? Depending upon what book you read or what literature you read, there are other ways to classify, right? One is diffusion coatings. We briefly touched on boronizing, aluminizing, etc., etc. So some are inwardly grown coatings, yeah? These are diffusion coatings. Some are overlay. This is easy to understand, right? What does overlay means? It's sitting over a substrate, correct? So in one case, you almost have no change in the dimension of the part, and the coating becomes an integral part of the substrate. Yeah, in these overlay coatings, you actually deposit something on top. Yeah, there is almost no interaction between the substrate and what's above, although depending upon what technique you're talking about, there may be some interdiffusion at this interface, but other than that, the properties there and there are very different. Yeah, and coating by and large remains a separate entity from the substrate. Yeah, so you can see the differences here. Look at the scale little bit. I mean, when we talk about diffusion coatings or altering surface chemistry, you can, depending upon what kind of treatment you do, you can go to a fair depth underneath the substrate surface, and then there are all these other techniques, right? Some you will see them classified as thin film. Even 50 is a stretch for that. You normally want to go just 5, 10 microns, 15 microns. there are thick coatings which go to several mm, and then there are overlay clads, PTA, etc., which can go thicker, right? So it's a busy slide. It's accessible through that QR code that you have been provided. It's in the stack of slides that you have. So don't bother to read so much. The point that I want to make is all of these coating families, I'm calling them families now. Yeah, all of these families of coatings are different in many, many respects. Yeah, since it's so busy, I don't want to go to every one of them. We just saw how their ability to deposit thicknesses can be very different. Some of them are done overlay coating, some go inside your substrate, some are outside, and they also go to different extents, right? How much of a diffusion layer you get, how much of an overlay coating can you deposit, yeah? So they differ in that. They differ, as I said, in part temperature. Some are extremely hot, yeah, more than 1000 degrees even. Some are pretty cold, almost nothing happens. So in these kind of cases, you need to worry about how long it will be at temperature. Are there issues related to distortion you should worry about, and things like that, right? Many times surface finish is also crucial, right? Good finish. Some of them are pretty rough. We spoke about roughness in EBM and SLM yesterday, right? So can you live with a rough surface? Do you need polishing or some kind of finishing after you coat? So all these become obvious issues when you start making decisions, right? So again, quick summary. If you look at status of surface engineering today, I hope you agree based on what I showed, that you have a very wide choice of coating processes, coating materials as well. If you combine everything that was on earlier slides, you have a very wide range of both quality and cost, yeah, and that is important. You need on the road for different kinds of guys. You need BMWs and Mercedes. You also need a cycle and a moped on the road, right? Because different people need that, correct? It's the same with applications. Some applications may not be able to afford very sophisticated surface treatment, right? But they need to be treated in any case, right? So there are very cheap ways of treating surfaces. There are very sophisticated ways of treating surfaces, right? And you need to have an open mind, yeah? You got to believe that even something like a razor blade can afford a diamond-like carbon coating with metal doping, right? Because there's a market for it, yeah? Because the life extension is by more than an order of magnitude, if you can put that on, correct? So it's important to know that this kind of a portfolio exists. I hope you also acknowledge now that it is highly versatile. We spoke about corrosion, wear, thermal barrier, aesthetics, everything. So you can accomplish all of those. And this is growing. I mean, I will show you some examples where we are going with surface engineering, and it's great to be in that situation, right? But if I want you to remember one thing, I will once again say that these are non-competing techniques, right? So that you should remember. My take-home message is that for young minds, right? So no single technique is universally applicable, correct? So that's important to know. People like to map different things in different ways, right? So if you begin to map how these different surfacing technologies stack up, and let's say you want to map it on surface temperature during surface modification and the ability to deposit thickness of a certain kind, yeah, you can draw maps like these, right? Weld overlay, right? fairly high temperature, but you can build very, very thick, yeah, several implantation. It's sitting in this corner, yeah, it struggles to modify under the surface up to 1 micron. You will never get there beyond that. Not such a hot process. So depending upon the type of substrate, this can become an important consideration there, right? Type of substrate, type of application. So you can then begin to pick what suits your requirement, right? Let's also look at little bit how the coatings have evolved. Very early time, right? Most coatings were single component, right? Someone mentioned galvanizing, yeah? Even metallization, you would spray aluminum or zinc or very, very simple materials like that. Over a period of time, and this was pretty quick, you transition to multi-layer coatings. Even a normal thermal barrier coating, maybe the techniques were old, but people realized long back around 1960 that you needed a 2-layer coating, right? A single layer will not do. You cannot put, for example, an insulating zirconia or something, right? Because it still left the substrate open to oxidation, because zirconia is permeable to oxidation, right? So you can get the insulation, but oxygen still goes through zirconia and then oxidizes, right? So that was just an example where you realized long back that 1 layer will not do, right? So multi-layer, multi-component coatings, I will not even say recent. We did that quite some time ago. Now we are already at gradient and nanostructured coatings. Our ambition also has changed, right? Initially, people were worried only about cost. Now more and more you worry about sustainability and say no more hexavalent chrome. We won't use that, right? So our ambition also is lightweighting, especially in the automotive industry. Lot of desire at least to transition to aluminum and magnesium alloys, but they are lousy. When it comes to corrosion and wear, they are not good, yeah? So you need to look at coatings in the context of your desire to lightweight. Then tailored functionality. Maybe somewhere along the way I'll talk about that, but fortunately you are now in a position to tailor properties the way you please because of what is available at your disposal. Future. What does future hold? What's your ambition? What kind of coating would you want? If you are a dreamer, if you're dreaming, what kind of coating would you want? I'll ask you first because you're always gassing, right? Tell me, what kind of coating would you want? Anyone? Just dream big. What kind of coating? I may say self-healing, right? Something is cracking and I want the coating to heal itself, yeah? Something like that. What is your dream for the next kind of coating? I have 2 dreams which I know I will not realize. One is self-healing. Second is what I like to call chameleon coatings. At least tell me what a chameleon coating may mean. If I change colors, very good, but wrong answer. Yeah. What's a chameleon coating? If I say my dream is to have a chameleon-like coating, change in properties, correct. If it's operating at room temperature, for example, I would want it to behave in a certain way. If it operates at high temperature, I would want it to behave in some other way, correct? Can we do that? I don't know, but that's my dream. But I'll surely retire before that. So the possibilities are limitless. And you should dream big. I think that's my message, right? If you went back 20, 30 years or something like that, you would have already begun to see applications and multiple applications in all of these areas, right? So, this has been for a long time the playground for all kinds of coatings. If you look at Formula 1, Formula 1 has been a playground for all crazy things, because why? Why is Formula 1 a good playground? How many of you know Formula 1 in the first place? Yeah, all of you know, many of you know Formula 1. Why is it a good playground? Because nobody worries about cost, right? You're only worried about performance, right? So, whatever the cost. So, many of the coatings in automotive, for example, what are used all the time today in passenger cars, were actually started in Formula 1 cars, right? And then you saw the performance, and then people said, oh, I want it in my everyday car, right? Which is a challenge, because especially the automotive industry wants much better performance, 10-year warranty, lifetime warranty at zero cost, right? So, it's a very competitive market, right? But many of these coatings are real today, and they came into being because of Formula 1. So, anyway, coming back to the point, these were all traditional industrial segments that used coatings. But if you look at it today, it's unbelievable. I would never have thought that something like a Gillette blade would have such sophisticated coatings. And coatings are equally sophisticated in all of these things, right? Even this cookware, right? Implants. This is a good example of hybrid, for example, right? I would call this hybrid manufacturing really, because now you do use AM to build patient-specific implants depending upon age, size, etc. And then you put on a coating, yeah, to improve fixation. What is fixation? Yeah. Let's say you are having a prosthesis joint here. Why do you need a coating? Does not react. Why do you need a coating on a prosthesis joint? Long lasting. Subjected to wear. Yeah. If it's here. Okay. So, many different reasons. People started with stainless steel implants, right? And then they went to titanium alloys, right? And the reason to migrate to titanium alloys was biocompatibility mostly, right? And then you found that you still need something else, strength. In case of titanium, that's true as well. It's lighter, strength to weight ratio, but they still felt that your fixation is not good, right? So, people started looking at coatings like hydroxyapatite. Yeah, how many of you have heard of hydroxyapatite? Hydroxyapatite is a major component in at least two parts of your body. One is all the bones have lot of hydroxyapatite, your teeth have lot of hydroxyapatite, right? So, inherently biocompatible. That's why they looked at hydroxyapatite as a material. But what was the focus at that time? They wanted a porous hydroxyapatite coating. Why porous? So that your tissue would grow into the pores, and therefore fixation is better, right? So, you can imagine how life evolves, right? So, you first wanted implants, then you wanted lighter implants, then you wanted biocompatible implants, then you wanted better fixation. Now, after all this is done, people said, oh, if it is porous and if it is load bearing, the implant, then it may not take wear, and prosthesis is a good example of that. This is load bearing, right, compared to, let's say, putting it here or somewhere, right. So, it evolves all the time, and therefore very sophisticated, correct, to provide the kind of coating you want. This is another example. Maybe if I have time, I'll talk about some of what we did at ARCI during my time, yeah, in terms of providing multifunctional coatings there, yeah. Am I going too slow? No? Okay. So, let's spend a moment or two talking about how do you ensure that your part is successfully surface engineered, right? There are a few things that are absolutely crucial. You must have a good comprehension of what the design criteria are, right? You must understand the application environment, absolutely crucial, and use that material and select an appropriate process. If you go back to the busy table that I showed, yeah, other things could also come into being. You must also understand your component better, right? You need to know the geometry of your component, size. Is your coating process then line of sight? Thermal spray, because I will perhaps talk about thermal spray more tomorrow. Yeah, it's line of sight. So we have industry coming in all the time saying, oh, I have a pipe which is 10 meters long and about 2-inch. So all that is part of your process selection. And then there is implementation. Handling is very important. The reason I am smiling is now because of my old age, I remember many things that I have seen in life which are absolutely terrible. So preparing the part properly, I recall that one of the first real life components that I did was during my time at DMRL. We were coating the interstage before it separates. It had to see a high heat flux, and of course that was a very high visibility job. So all the VIPs who came to DM, what we were doing in the thermal spray lab, and we had fresh the interstage, right? Because that's for thermal. I will talk about that tomorrow. One is to create a rough surface, because all these coatings are mechanically anchored. The second is to ensure that it's an oxide free and clean surface. This is nice and rough, yeah. Ooh. And you're not supposed to touch these parts. Some greasy stuff from your finger. So that's very important, right? Handling the part also very. We had never been to any. When we got drawings, we did the coatings. At the time of installation, I mean, at least thermal spray coatings, they do everything else very nice, but they don't take impact away. And this guide van has to come back from Himachal to Hyderabad to recoat. So, yeah, some not so pleasant memories of. And then I put up this pretty slide. Busy slide. Busy slide. I hope it's in your, is as follows, right? Environment for as long as you want it to survive. Environment for as long as you want it to survive, right? And then once you have identified those requirements on the surface, the next thing you do is explore if you can find a one-piece construction. Can you find a material that will fulfill all the bulk property requirements and be able to withstand the working environment for the kind of time that you have, right? If the answer to this is yes, you are in good shape. Don't even worry about coatings, right? But unfortunately, the answer is very rarely yes these days, right? Because we are becoming greedy, right? We want better, faster, or whatever, right? You can look at how the turbine temperatures have increased, right? We have gone from 1000 degrees, 1100, 1200, 1300, still not enough. And there is a reason, because what happens if, why do you want to do higher temperature in a gas turbine? What go higher in temperature? Some of you guys. Which means what? Explain in plain English to younger guys. Correct. Yeah. So everyone is chasing efficiency, and therefore you want to operate turbines hotter and hotter. So what was good on a turbine several years ago is not good today, because that ambition is changing. If you look at maybe 1960, 1960, there were thermal barrier coatings which were flying, yeah, but they are sprayed using, believe it or not, an oxyacetylene torch, yeah. Today, if you say I'll use an oxyacetylene, you will be fired on the spot, right? So things have changed a lot. As I will talk tomorrow, you will not believe what are you looking for from the coatings, what are the constraints. Those constraints could originate countries in the world. What kind of processes would be appropriate. So if you are working in the lab, most time your job is to rank how these process material combinations work. If you have shortlisted and still have a window to decide, you use different materials of choice, different processes of choice, and rank how they perform before taking a decision, right? It always helps, apart from other things, if you have some idea of what the failure mode is, right? So if there are some PhD students out here, it's not enough if you do a tribo test, yeah, or a wear test, or a corrosion test. What do you do after that? What do you do after doing a ball on disc or a pin on disc test? If you are looking at it, wear, or even corrosion, yeah. Let's say you do a salt spray test. What do you do after that? Anyone? Correct. You do a post-test characterization, right? So that is almost as crucial. Why it eventually fails, because that's the only gateway to make it perform. Look at what all you can change today. We would normally have corrosion, and can change any property on the surface. We already indirectly things, yeah. We can modify electrical properties. We talk about yttria, stabilized zirconia. I was materials and processes, right? So as a smart design for TBC and how you go about making, to give that example, make here, right? So what's the primary purpose of a thermal barrier coating? To go to temperatures which are higher than the substrate would otherwise allow. Yeah, you want some insulation so that you can operate the engine at higher temperature. The other purpose, because you are talking about higher temperature, is also to impart oxidation and corrosion resistance, whatever may come, right? In some cases, oxidation may be predominant. Why do you think I say that? Because you have a clean fuel environment. In some cases, you have a dirty fuel environment, right? If you look at land-based gas turbines, it's dirty fuel many times, right? So all that happens, right? Or simplify cooling schemes in a blade, for example, right? So you need all that. Requirements, right, from your application, correct? Now you slowly begin to select materials, for instance, right? Pick zirconia as the material, correct? Because it is one of the lowest, you don't want that mismatch, right? So zirconia is great, but what do you find? Yeah, that if you look at zirconia, you get monoclinic cubic other, it is accompanied by a volume change, right? And that leads to many stress. So you use yttria, stabilized zirconia, or something else, right? So that's tick off this bullet. It does not, unfortunately. It's a great material to you would like it to be. Yeah, your thermal is still a little bit different from the nickel-based superalloy. So you want something in between, which has an intermediate thermal. So you need that kind of a system then. That's how you pick materials. And then you begin to look at, okay, now I have decided YZ, how do I put it on? Much better now, right? Most people realize that that means I need a columnar structure, which can, and that's why instead of air plasma, it's a process, it takes time, and you as designers need to be aware of what's out there and how it has originated, right? So, plasma spray, EBPVD, and this is also almost 40 years old. Things that go even beyond this, right? So, this is part of in our lab as well. But yeah, you're continuously searching for new process. In general, now we are moving away from TB, could be of interest. You would want a certain thickness. You may or may not like the kind of roughness that you get is in case of additive manufactured parts, because in a coating. Bad. So give me an example where porosity is good. Give me one example of porosity is bad.
Good in sense
I will buy that, little bit reluctantly, but I will buy that. Just said for insulation you need columnar coating, so lot of porosity actually for insulation, and that's a bad example, wrong example. Anybody else? When do you? Corrosion, yeah, you want a fully dense coating. Most will do some sort of texturing on the for a cylinder piston. Those act as reservoirs of lubricant, right? So it's good, sometimes bad. It's for you to decide when it is good and when it's not. Mechanic will you do? This is the biggest challenge, right? How do you do this in a lab? And most good, yeah, but no, just joking. But assessing it in the lab, how do we prove that? How? If not, why not? Can we do this? Prove that coatings last over the lifetime? I don't know. Yeah, but yeah, test whatever it is, right? If you 100 degrees, bring it to room temperature, keep going till it fails, right? It could be different forms of wear, ball on disc, pin on disc, with stainless steel ball, alumina ball, tungsten carbide ball. We do all sorts of stuff. Yeah, same with corrosion. Yeah, salt spray, potentiostat, low temperature, high temperature. We do all these things. So these are all tests that you would carry out, but it is very difficult to extrapolate what you get in the lab with what will happen in real life. Very tough, and that's why it's a challenge. You just can't say I want a corrosion resistant coating. There are many, the point is that you need to come up with a do these coatings on small coupons. Look at microstructure. Look at, sometimes it's available in large departments with. So usually this is the sequence that you follow, but most it's okay if you just can do that, right? If you have collaboration or if your department is well endowed, you perhaps do that, right? And if you are getting amazing results, then the company will say, I will do this part for you, right? So, but that is what you need, and yeah, we are not going to get into QC and all that. But eventually that is, if you are looking for an ideal coating, that is what you would look at. You will ensure that it has the performance that you expect it to deliver, it survives for as long as you want, takes care of other issues which may or may not be important. Sometimes machinability, of course, you want a certain kind of, yeah, does it let you accomplish that? Does it meet your as a surprise, and is a big problem, not easy as it looks. One of the most well established coatings for wear, and wear is the biggest problem. A tungsten carbide coating, yeah. Your ambition always is that I must have a coating which will never come off, lifetime, right? It's, yeah, lifelong. No, that's not the case, but you want the coating to never come off, yeah. On which you have put on a wear resistant coating is a mating part, right? It made something. Usual roughness that you get with most of the coating techniques here is not okay, yeah. Then you want to finish it, right? And you can then imagine what a nightmare it is to finish the coating, right? Because you surface which is extremely wear resistant, and then you want to take material off from there, right? So very hard, correct? But you need to do that. This can be quite substantial, right? So quick recap. I can see that I'm kind of to summarize, I hope I have shown you that there are many ways in which where you don't add any external material at all. You the surface like alloying, right? And the third is where you add the material as a separate layer, completely separate layer, right? Some examples of each: laser transformation hardening. For example, a steam turbine blade. We have done some remelting, right, on cast iron camshafts, for example, right? Alloying, this is another, and yeah, you can also clad, etc. Yeah. So some of these techniques are surprising in how simple they are and what kind of property enhancement that it can give you. One of them is just using a laser beam to harden the substrate surface, right? I will not go into details, it's there in your slides, but let's look at three very typical carbon steels, right? EN8, EN19, EN31. The main difference in these steels is the carbon content, right? And look at the enhancement in hardness that you get by doing nothing except scanning a laser beam over the surface. You have not done anything else, right? You have not added any material, nothing. You just scan a beam on top, right? So it's a very powerful tool to, without adding any material, get very high hardness, gain fairly substantial improvement in wear behavior and things like that. Just an example, right? Something else we did at ARCI for the longest time and transferred it to BHEL later. This is a typical steam turbine blade. If you, we have spoken a lot about failure mechanism, right? Failure of these blades. It turns out that most of these blades fail at the leading edge because of droplet erosion in a steam turbine, right? We used the same laser hardening. It was a certain special kind of steel that BHEL was using, and we only scan this part, right, to improve life by at least a factor of 2, and then we passed it along to BHEL. So they do it in house. We did some limited production at ARCI. But this also reminds me of the challenge that one would face from a specification standpoint. There are specs. Some are pre-independent specs, like in this case. Very old specifications that BHEL had, because before we started this work on these blades, right? So most of the specifications were written for induction hardening. So one of the depth of 1.5 mm, yeah, because you almost automatically got that in induction hardening, and for us with a laser that was a nightmare. You can't get such a high case depth. You would begin to melt the blade. Developing or optimizing the process, our bigger effort was in convincing them that those specifications need to be changed. So many times you will encounter problems of that sort, and you need to deal with that. I ask them the most is, when do you consider your turbine to be unbalanced? Do you allow the blade tip to wear 1.5 mm before it? Microns, we are in deep trouble. Then I said, why are you asking 1.5 mm of case depth, right? So, but it's sometimes those kind of things are challenging. But laser hardening, very good technique. Same with the self to remelting, and very substantial improvement in properties if so And this is a great application as well, right? You can jump from one cam to the other. You can modify your use the right optics to modify your laser beam so that it's not a point beam, but it's a line beam. Yeah. So you can imagine you're rotating. Of course, it's eccentric rotation. Exactly matches the width of efficient than, for example, doing induction hardening. You can see why the rotation is eccentric, yeah, and you can see how if you did it right, so it's rotating, so the effective surface speed is different. Here to talk about, you should not miss an opportunity to go there if you are interested in surface engineering sometime. So what did we in various departments of ARCI? But I am showing this only to show that surface engineering is not within one lab. Can you believe it, right? In one lab we have all of these things, right, which accomplish different methods where you form coatings starting with a vapor, right? Yeah. So vapor is the source. It could be cathodic arc, it could be magnetron sputtering, it could be using an electron beam. It can be accomplished with something like chemical vapor deposition. There are tomorrow, but electro deposition, micro arc, sol gel, all these will not talk so much more, but of how big surface engineering is. Tomorrow we will pick just one of these technologies which in my view is closest to AM and talk a little more about that. But if you are hungry, we can take it another time. Yeah. Yes. AM repaired, but we are looking at repair in different contexts. Some of the repair requirements are for nickel based, and yeah, I don't think anything is qualified yet, but VWI, what's it called, EHLA or something, some high speed laser, yeah. So titanium 6Al4V. Similarly for in Cornell, we have been working on because there are many parts sitting next door in GIAN aerospace that need repair or they have to be junked. Everyone is talking about sustainability and that kind of stuff. So, anybody else?
Yeah, thank you. ఇక్కడే ఇక్కడేనా ఇది టచ్ చేస్తావు కదా మళ్ళీ చాలా ఇంత బెటర్ okay we'll start the actually we swapped the tomorrow session and today's session okay due to some restrictions we are going to do the experimentation for both the programs we are physically create the file for path planning as well as what design we wanted to print for tomorrow's and how to create STL file how printing is going to be taking place in PBF process and as well as in the WAM process and some post processing also we'll see in the tomorrow's afternoon and we'll go to lab but today we are going to learn regarding this end topology software how we are using to reduce the weight of the component in all the aspects either in the medical aspects or in the aerospace aspect or as well as in the automotive aspects or even in the fashion designing aspects why we require this minimizing the weight as we know already to improve the efficiency of the engines either the aircraft engines or to improve its performance by reducing the weight of the component by maintaining same factor of safety to maintain the weight and as well as to change the material properties or we can replace some other materials to maintain and as well as to reduce the cost of manufacturing how efficiently we can use this end topology to redesign the existing old component which is suitable for IT manufacturing process because we are already doing conventional manufacturing process their application of this topological design is challenging issues because we do not have that such kind of machining aspects because if you want to see some of the topologically designs curvilinear designs where we are like providing a support structures for our fabrication aspect such kind of supporting materials by machining conventionally it is very hard there was no facilities because we need to go either non-conventional machining or we need to go some kind of YDDM or some kind of water jet machinings or laser machinings and all such kind of process we need to use for those things but still we have a restrictions we need to create lot of fixtures for those things but how we can overcome such kind of designs which can be adapted by IT manufacturing that is what we need to understand by topological designs but no need to just redesign it but will it qualify the component that component can it be qualified for the applications simply with reducing the weight of the component is not going to suit for the application but how we can make it suitable for the real applications even after reducing the weight changing the designs which is suitable for IT manufacturing process and as well as suitable for our application orientation that is what we will learn in this topological aspects in the next session we will learn about this abacus or ANSYS how we can simulate this modeling aspects of our IT manufacturing process PVF or LDD process and all. Okay now our my student Srikanth is going to finish this topology he is a PhD scholar he has finished almost his work in this and he submitted thesis he is going to give how to train how to do the topological aspects of IT manufacturing okay thank you.
Am I audible? No, my voice is audible, right? Okay. Okay. Good afternoon to all, and thank you, sir, for the brief introduction about the weight reduction methods and topology optimization. And today we are going to see the weight reduction methods, how we can reduce the weight using. There was one software called which is N topology, that is advanced CAD software. Specifically, it is like a how traditional CAD softwares are different, and what we are teaching that is different actually. What is the difference? We will see. And first we will see the weight reduction methods, and we all know, okay, 3 weight reduction methods are there. One weight reduction method you all know, what is that method? How to reduce the weight, something like that. No, like we all know means like by seeing like has a 10th class to 10th primary guy also know like so which is heavier, like there is a one question like the steel or 1 kg cotton which is heavier. Both are same. Then 1 kg steel or 1 kg or aluminum which is heavier. Both are aluminum we have seen, right? Suppose you have a steel and aluminum is there. and like volume is there, like 10 mm by 10 mm steel is there, and 10 mm by 10 mm by 10 mm aluminum cube is there. Later, right? That is called, that we call the material. Like by replacing steel with material, that we call it as a lightweight material. And one method is the material substitution. Like by replacing the material with the lightweight materials, like aluminum, titanium, we call that as a material substitution. And the second method is called the structural optimization. In the structural optimization also 3 types of optimization is there: topology, shape and size optimization. Mainly like people are focusing on the topology optimization. Right now the current trend is going on the topology optimization, that we will see, I will tell you. And the third one is the lattice structures. Lattice structure means this is not a new term to us, this is like a, and the even topology optimization also very new to us, I will tell you the difference. And the lattice structure means we have heard about the lattice, forget about the structure or something. Lattice, where we heard about the lattice? No. Like in nature we have had, like in chemistry we have had, right? Crystal structure. In chemistry we have had BCC lattice structure, BCC crystal structure, same thing, FCC, same thing. The inspiration got from there only actually. We are getting the inspiration, the lattice structure there only. And we will see that how the lattice structure get inspired also. And the classification of the lattice structure we can see strut, TPMS, planar, we will see the difference between all these things. And we take quick slides. And this is a material substitution, this is the old like during old method, old method, it does not mean that we cannot use right now, we can use, but previously long back we are using the material substitution. Currently people are using the structural optimization, and in future like maybe in space or some in SpaceX or NASA, these people may use a lattice structures also to reduce the weight of the component and improve the efficiency also. And for like this is the weight reduction, right? Why we need weight reduction actually in general? Take an example and why we need the weight reduction. Take any example. Forget about the aerospace or automotive, forget about it. If you know any example, you just quote an example to me, so that I just want to.
Just take a passenger car. We want to reduce the metal sheet thickness. Then as you said, weight will reduce and fuel efficiency will improve.
Yeah, fuel efficiency will improve. As he said that if I like car, he said right, automobile, right? In aerospace there is one problem is that, I mean whoever traveled in the flight they might know this thing. Actually in aerospace there is a problem with the fuel consumption, because in between air, for like in automobile in road only we can fill the air, but in between air we cannot fill the air, right? So what they will do means they will calculate each and everything, they will calculate each and every weight, like they during the check-ins also the luggage is there, overweight is there, they will send it to some other way, and if they ask overweight is there, we need to reduce the weight and all those things, like check-ins is there happened, right? Why they are doing this means just to check this, just to fill the fuel only actually. So in between we cannot fill the fuel, right? So aerospace 1 gram of reducing the 1 gram of weight also very important, like it will improve the fuel efficiency also, that fuel cost also very high actually. So that's why we are getting a like flight tickets are very high because of this, and they are reducing the weight constraints are there actually. And the factor of safety there, just remember that in buses we are getting a factor of safety, like factor of safety is there is no extra passenger, something like that. Whoever the passengers are there, that will be fixed actually, there is no vacant of the passenger are there. That is the factor of safety. Aerospace is 1 actually, they should strictly follow, there is no like no not 1, like some 10 or something like that. But in buses or something, factor of safety you can go for 0.8 also, like we are going beyond the limitation of the passengers, right? That will be, but in aerospace they will take the huge number of factor of safety. So the structure should be very high strength to weight ratio. So that is the future, and these are some of the lightweight materials. But the first one is the past one is the lightweight materials. Right now people are using aluminum alloys, like shootable AM process also we can see, and where we are using the aluminum, mainly titanium alloys we are using the aerospace and medical implants actually. And this is the shootable AM process, you can see it. And the composites, polymers, ceramics, these are the lightweight materials, and the shootable AM process also we can see, okay. And this is the, I told you right, aerospace and automobile body, this is the composites we have seen, steel, aluminum, steel and plastics they are replacing just to reduce the weight. This is how the car body is designed, and this is how the material get replaced, okay. Yeah, the question is that I told you the topology optimization, right? there is one more like one side of coin topology optimization is there, and the other side of the coin generative design is there. Mainly people means the designers who are working on it, they are getting confusion. Let me clarify that generative design and topology optimization are like a apple and oranges, not like apple and apple, okay. Both are not same, means both are like a different, okay, but they both are on the two sides of the coin, okay. So what is the meaning of the first? We will go for the topology optimization. It will be very interesting, like you know this thing actually, like don't combine the two words, like separate the two words so that you will get the definition, okay. Like one is like a topology, other is like a optimization. So what is the meaning of topology?
Nature of surface.
Surface, okay, like in terms of design it is there actually.
Features of a surface.
Surface is okay, like okay, I will tell you, topology means geometry actually. As a design in the, like topology means we like yeah, topology means geometry, and the optimization means, okay, why we need this one we have had optimization, like you are not optimistic person, we like that we are had about this thing, right, and the optimization also we have had. There is one term called, whether you know or not, SEO. How many of you know SEO? SEO, search engine optimization. Have you heard about it? Yeah, search engine optimization means, okay, then what is optimization there? Optimization, we might have heard this thing actually during the industrial subject, like optimization means finding the best, getting the best, right, getting the best, optimization means. And search engine optimization, what they will do means, Google is the best search engine optimization compared to Bing and Thor, these things. Why, how they will proceed means, they suppose you are searching a one product or something, you are searching something like what we call something, you are searching a product, it will give you the best results actually. The unnecessary results it will avoid it actually. So that we call it as search engine optimization. That should be, SEO engines should be there actually there. So finding the best, and we suppose in short example, if I say this means finding the best means, in Flipkart you might have seen the, okay, optimization will go it, then what we will see. Optimization means finding the best, your objective is to, suppose in Flipkart your objective is to buy a laptop or the mobile. So you need a specifications, your objective is to buy a mobile, okay. So you have the specification of your objective is the buying a mobile, and the constraint is that you have the cost constraint is there, and the RAM and the like color and these things are there. So that we are fixing the constraint, means filters we are fixing, and the objective is the giving the mobile. Suppose if you are searching a mobile and it won't give you the laptop, right, it won't give the results of the laptop, right, we are searching a mobile, right. So the filter we can do, that is the constraint we are doing, so that it will give you the finding, it will give the best results, so that we can choose one, right. Same thing will work on the topology optimization also. Same thing means our aim is to, our objective is to reduce the weight, and means reduce the weight, not only reduce the weight, we can reduce the weight at any possibilities, but improve the strength to weight ratio. Our objective is to improve the strength to weight ratio by using some constraint. That constraint may be, it should not exceed the factor of safety, mainly factor of safety should not exceed more than 2. If it is exceeding more than 2, we can reject the sample like that. So it should not exceed factor of safety, means yield strength, it should not go beyond the yield strength, like that. These are the constraints. And the deflection, it should not deflect, the optimizer geometry should not deflect. These are the constraints we are fixing, okay. So that we call it topology optimization. And the generative design will also work for the same thing, objective constraint will give the best result. But the problem with the generative design means, you might have heard the design, but again separate the two terms. We might have heard the generative also. Recently this term is got popular actually, generative. Have you heard about it? No, generative term is recently popular right now. Yeah, ChatGPT, right? Generative AI. What it will do? Generative AI means, like we are entering some prompt or text we are entering, it will generate the text, whether it is correct or not, that is our concern. But AI, it will works on the artificial intelligence, right? Like we are entering a prompt and it will generate some information, answer. The same thing will work here. Generative design also will use the artificial intelligence program, and the topology optimization will use the mathematical algorithm. Means the software can be we are inserting with the mathematical algorithm inside it. In generative design, suppose like ChatGPT is there, right? If the internet is not there, will be able to work on, will be able to get the information? No, right? Same thing will work for this also. Like it won't work on the offline actually. The software, I mean I forgot to say the software. Generative design will work as per my information. Generative design work for only in the Fusion 360 only. Autodesk Fusion 360, there is a education license is there, you will get it for 1 year. And the good thing is that after 2021, I think we for education license we are getting unlimited cloud credits, so that we can generate any number of things. Okay. In the topology optimization, there are huge like whatever the software, CAD software we have, all work for the topology optimization only. Only one software that is working on the generative, means artificial intelligence using this generative design, that is topology. So clear, right, the difference? Now the person got this, that was the confusion is there. So difference between that. Okay, we will see some of the examples, and you can, I mean right now you may not identify the examples of the which is generative and topology, but once you go through the software, then you will able to identify. Once you see, you will able to identify. This is some of the examples, real time examples where we are using. See, this is the nature, like we structures, we all get inspired from the nature, right? Like I said, lattice structures, crystal, BCC, these things. Same thing. This yeah, forgot. Like sometimes, like we are optimizing the material, means optimizing the, here on for the time sake I am saying optimizing the material, sometimes for the aesthetic purpose also. The main motto is to it should serve the purpose. Like the thing is, suppose you are sitting in a chair, right? The chair will be like this, but if I remove somewhere in the material which are not necessary, I can lift easily, right? So that I can lift the weight, but it should serve the purpose. Like you need to sit comfortably, right? The thing is, it should serve the purpose. The performance is useful in the aerospace and automotive. There it should not serve the purpose, it should serve the purpose, it should improve the performance. Okay, that was the we are getting inspiration from nature only. Okay, yeah. What is this bike? Yeah, everyone know, right? Because of the color orange and black. Okay, that is that structure is there, right? That we call it as a topology optimized structure. The material, we are previously, like I don't know about it, like but the structure is we are removing the material inside, that we call it as a topology optimization. This you don't know. I mean this was, I think 1 month back, they have recently implemented in the Ferrari car actually. Ferrari F80 sports car. They have implemented, they have 3D printed this. This is suspension system, like this is a topology optimized suspension system. I told you, right, it will just improve the fuel efficiency and all those things. Ferrari F80 car, yeah. And this one, bike name, I think logo you can see, maybe Royal Enfield. No, this is a recent bike only. Recently in Delhi Auto Expo they put it. No, this is electric bike, Royal Enfield electric bike, Flia, Royal Enfield electric bike, and the structure you have seen, right? This one, that we call that was optimized actually. And here also that design is there, right? Maybe because of the brightness you might not see. Here you can see that was optimized, topology optimized, so that to reduce the weight only. And this one, chair, furniture, right? That was generative design actually. That is not topology optimized, that is generative design. As I am working on it, so that I can able to recognize which is generative, which is topology. And this one, generative. I told you, right, that should serve the purpose, but be it strength or forgettable, that should serve the purpose. Here it is serving the, like sometimes like aesthetic purpose, like looking wise it should be good, like that. Generative design, okay? Yeah, that one. And what is this, like some generative design is there, right? I look forward in time and saw the 14 lakh some features we have seen, like Dr. Strange told to Tom Cruise, right? Sorry, Iron Man, right? So CAD engineer will, the same thing will work for the generative and topology optimization also. I will show you the example so that you will come to know. See, the original design is this one, and what it will do means generative and topology optimization, the algorithm may be different, but the thing is the purpose of this thing is same. There we call it as a number of iterations we call it as a, till it get converged. Number of iterations is there, right? 1, 2, 3, 4. Here due to the space limit we have shown 4, but it may give the some thousands of designs also. It will generate actually thousands of designs, so that we can finalize one design. Whether that is satisfied or not, in that software it will automatically give the table and chart, it will automatically give. We can able to select whether we can choose this design or not. And this is a sitting chair, we can see original design is there, like we are that should serve the purpose. This type of designs is already existed, like we are seeing the table chair and all those things, right? So how many possibilities we are getting means only one we are getting, only one we can choose, the best one we are getting, the only one, okay, till it get converged, okay. So the next thing, okay, next thing is lattice structures. So lattice structure means what is the meaning of lattice? Okay, forget about the lattice. Is say okay, I can say porous structures. Lattice you might get confused. Porous structure means some pores, holes should be there, okay. Hole type of structure, material removal, okay. So what is, okay, you got inspiration, I told you, right, like BCC and all those things. There are some other things also there that we will see in the inspiration where we get inspired. Like, okay, first of all, what is the meaning of unit cell? In lattice structure, like suppose he might have see the Rubik's cube, right? How many cubes are there like that? Rubik's cube, we are playing with the Rubik's cube, right? Different color Rubik's cube. There may be 3 by 3 by 3 or also 4 by 4 by 4 also Rubik's cube is there, right? Means 64. That one cube we are extracting, right? That we call it as a lattice structure. That is repeating, right? And you can see here holes is there, right? Holes. That is repeating, right? Like X, Y, here this is the 2D holes. Like X, Y, Z, it is repeating. The same hole is repeating, right? The same thing. Rubik's cube also, the same size of cube is repeating in the X, Y, Z direction. That one piece of unit is there, right? One piece of unit. Like in derivatives we have seen, right? Suppose if you want to calculate the area of the surface or something, we are taking a one piece and we are integrating. The small piece, we are integrating. That one piece is called as a unit cell. And we are calculating that one piece into like that, okay. If we see that, then we will come to know in the NTOP software this is there. And why we are going for the weight reduction means aerospace alarm due to reduce the fuel consumption. In biomedical also it is there actually. Why? Like I will tell you the example. This may be the good or bad. Like some people know, like we are using some legs prosthetics is there, right? Prosthetic in olden days some legs is there, I think so. I mean I don't know. We call it as a Jaipur leg, something we call it as a. Is it still there? That is the correct one. Jaipur leg only, right? I don't know why they call Jaipur leg, but they call Jaipur leg something like that.
Why it is called Jaipur? Because the doctor who created that, he is from Jaipur.
Okay. So okay, it is familiar word only. Jaipur leg is familiar. Okay. Because my father used to call like that. That's why.
Actress, even Bollywood, she uses that still.
Okay. Yeah, Jaipur leg they are keeping this one, right? So that will be very heavier actually. Suppose if you are walking this means we can't able to bear our foot, right? That will be very heavier. There the weight reduction is very important. So what people are doing, biomedical engineers are doing, they are adapting the lattice structures. Like prosthetic arms they are designing actually. And some cement we are doing this thing, right? Like cement joint something like that, right? They are doing the prosthetic arms, and mainly biomedical implants they are applying this one. Biomedical implants, how they are applying means that should match lattice structure. The good thing about the lattice structure means suppose we are getting a material aluminum we are printing, right? Aluminum, the properties are same, stiffness, Young's modulus. Whatever you have designed that is aluminum, so the property is same. That will not change. But the good thing about the lattice structure means if I printed the different lattice structure, the property will vary. It won't depends on the material. You might have say like while studying the lattice structure, suppose if I printed the lattice structure with aluminum or some PLA material, we are getting the characterization, mechanical characterization we will do. The Young's modulus is there, right? The Young's modulus need not be same as the aluminum material because that is not a standard method. Standard method is the tensile specimen. So the Young's modulus is varying. The good thing is we are using this in the bones and all those things because that Young's modulus should match with the bone. Bone modulus is there, right? Because like that we are varying the properties and we can finalize it, which is good actually. There is a research is going on it actually in lattice structures, mainly in the biomedical bone, that we will see. how to, we will take that as an example, bone, and how we are designing with the lattice structure in n-top. Okay. So this is the inspiration. How many of you recognize the first one? Which one? I think I have written the name. Okay. Okay, crystal structure. This one? This one? Yeah, fish is also correct example. Like there is one, I think, in rapid prototyping, I think recently published, fish bone something, one type of structure they got inspired. That also right. So this is butterfly wings. And this one? Yeah, bone, if you cut a, like our bone is there, right? If you cut inside it, we can see this cross section. And the third one? Yeah, architecture. Can you see, can you rename other example than this? Like this is like in ancient days they will build this type of architectures. Why they will put, like this holes is there, the pattern is repeating, right? Why they are keeping just for the ventilation purpose? Because we cannot keep everything as a solid, right? There is no ventilation, right? So they will keep inside. Their repetition pattern, lattice structure, like porous structure, something like that. We are getting inspiration from there also. And one more thing is Eiffel Tower is there, right? That we call it as a, why not give, that can be a solid or something, like trusses is there, right? That, yeah, trusses is there, right? Why can't we keep it as a solid? Just to ventilation purpose and to improve the strength and all those. Okay. This is the geometry variation. You can see the geometry variation, how it is varying the, as I already told you, right? See, from bottom to top the structure get varied, it should not be same. Okay. And you can see the, here in hexagonal the property is not changing, hexagon, square and reentrant, it is not changing the cross section, means that is the 2D lattice, remaining are 3D lattices. And the bottom is, in bottom 4 is called as the TPMS lattices. Okay. And the applications, I told you the example, right? Application of this one, aerospace or biomedical, defense, energy, these things. This is how we can use the applications. And this is some of the app which I did, like lattice structure applications. You can see the, all these things are the applications of the lattice structure where we can use in different categories like sports and fashion design and engineering, home appliances, these things. Okay. So yeah, this is the project which we did, lattice structure applications, and we should acknowledge them, like we, because of them we completed our, I mean specifically our research got completed very quickly because of the, they have provided something, we have explored these many applications and we found it should be interesting. So I just want to share that, we shared that. Okay. And this is about me. So with this quick introduction we can go through it like n-top software. You have a, you get a clarity about the lattice structure, right? Any doubt in it? Like anything, if no, if nothing is there we can go for software. Okay. So you are able to see, right? Screen, black, dark mode I am using. Okay. You are able to see, right? So and this is the n-top UI you can see here, and mainly we are using for the, as I told you, right? Just a quick glance about the n-top I will say, like UI I cannot able to touch due to the stipulated time, like, but the main mode of the n-top is just to design the weight reduction designs, and means topology optimization, be it a topology optimization, be it a lattice structures or anything. And the why n-top with AM means, if you are working on the AM means and some good structure DFM or something, then you should familiar with this software, because there is a lot of opportunity, like in future I am saying, in future there is a lot of opportunity that can be explored in this software. This student license we are using, we got a student license, we are using that only, and for not for the commercial purpose, like we are using for our research purpose we are using. Yeah, if you want to explore the research purpose you can apply for the license, they will activate it. In the website it is there, n-top website it is there, you can apply for the license. We are using for the, not for the commercial means like selling or purpose or something, just for the research purpose only we are using. No, that is different, that is for generative design actually. This is different, this is for lattice structure and topology optimization. Yeah, Autodesk Fusion will be different, yeah, both are different, don't get confused. Okay. NTOP means formerly known as N-topology. Now they are keeping the rename as a NTOP. Okay. So the main advantage of this means in additive manufacturing, they are like suppose additive manufacturing we are there, right? So additive manufacturing brings the complex structures, right? This will give you the complex structures like organic shapes are there, right? Organic shape, bionic shapes. That will like in the beginning of the slide you have seen the example, right? That Ferrari, these things that we cannot able to manufacture with the subtractive methods. So we are going for additive manufacturing. And the lattice structures also, that is very precise geometries is there, and there we cannot produce a die or something. So we can complexity free geometries we can able to print with additive manufacturing. That complexity will take care of this NTOP. Okay. So we will take an example of the, I will tell you how to generate a lattice structure, and the inside like the properties, mechanical property, that is again deviating from the research, that you can find it in the, like I will introduce about the software, how we can generate the lattice. Okay. And I already told you the unit cell, all these things, right? That I will show you. Yeah, NTOP, one more thing, NTOP will work on the, I told you like traditional design, and there is a lot of difference between NTOP and traditional design, CAD design. In traditional CAD design like SolidWorks and Creo, what we are doing means we have a 3D model diagram is there. Here we cannot able to means 2D sketches, we are getting a 3D models, right? But here it is not like that, there is no 2D sketches or something. Okay, that's why there is no plane, front plane, top plane, these things. That is for the, this is here there, that is for viewing purpose only. That is not a plane or something, don't get confused. Okay. So for 2D sketches we are using a planes. Here there is no 2D sketches. Once we have a 3D model, we can play with the 3D models. 3D models means original models, I am saying. That original models we need to design in the SolidWorks software. Okay. Be it a cube or something, cube, simple things we can get it. Cube, a cylinder, these things, sphere we can get it. That we can get it here. But the like tensile dog bone specimen, that is the sketch should be involved, right? That we can design it in the SolidWorks software. So first I will tell you with the cube from this software, and later I will take the tensile specimen, and now we apply the tensile specimen on the what we call gauge length, that I had designed in the SolidWorks, and later if time permits we can go with the bone or some automobile application, brake pedal, where how we are applying. Okay. And this is like a implicit body, it will take like suppose, I mean this is a laptop, suppose if you are working in the some high configuration system, the good thing about this software means like we are getting in SolidWorks BCC lattice structure we can easily design in SolidWorks. You might have find the videos also, but the problem with the SolidWorks means one unit cell we will design it, and we are patterning into 3 directions. But the problem is that, what will the problem is that we face this problem, personally we face, that's why we are saying like the problem is it, we are repeating, right? The system configuration, the system like processing will be very slower, it may dead also. So we need to save it continuously, and the file size we are getting is very heavy, higher file size, like it may be exceed to GBs also, that if we give it to computer or some slicing software, it won't even take the software, we need a high-end systems. That is the problem with the traditional CAD, but implicit models is not like that. Implicit model there is no faces, selecting faces or something, we will take everything as a single body. Okay. So with this we will go with the lattice structure. There are again 3 types of coordinate systems are there, like rectangular coordinate system, cylindrical coordinate system, and spherical coordinate system, right? We will use the rectangular coordinate system and we will generate the lattice structures. Okay. See here I see modeling and creating this you can also explain like that, anyway I will use it here. Okay. See lattices is there, right? Lattices means we will use the rectangular coordinate system, you can see here rectangular, cylindrical and spherical coordinate system. The shape will change. Okay. Spherical means we can use only for spherical, it is not like that. Okay. So rectangular coordinate system, and it is asking, once I press the rectangular coordinate system lattice, rectangular lattice, it is asking the like optional, you just remove it, leave it, and empty means it is necessary, we need to keep something here, there. Okay. See volume, it is asking, volume means what is the volume? Original design. Okay. Original design, that should be implicit body, not CAD body or something. CAD body it won't take, that symbol is there, right? Icon, that is implicit body symbol. Okay. So if you are getting a confusion or something means, okay, further we will go. Okay, first method I will tell you how to recognize, since if you are a beginner in the NTOP, how to recognize means I will tell you the first method, later method I will tell you next. Okay. If you are a beginner or something, the first method is that just long press on it, it will give you the available options here. See, it is giving available options, these many available options it is giving, right? means this black, this green color indicates the all are the implicit bodies, okay, Boolean intersect or something, but we need a implicit body of the cube or sphere or something. So just type it here, okay, long, like double press on it so that you can see the available options, or otherwise just type what type of design we want, like cylinder or sphere, cube or something. Suppose I need a cube, I will press it here, will automatically give you the cube. See there it is giving cube, right? So what is the size of the cube you need? It is asking. Means the cube position is in horizontal. I am origin. I am not changing that. What is the size of the cube? It is asking. So I will take a 30. Okay, 30 mm cube. So this lattice size I will improve more because of the processing time get reduced. So I will take it as a 10, 10, 10. Let's see. Acha, tell me like unit cell size. Okay, okay. First, okay, anyway, I didn't care. Okay, first we can see the unit cell. There are three types of unit cells are there. One is like a strut based. Strut based means BCC, all the strut means rod type structures is there, right? Rod, strut, we call it as a strut. That rod is called strut, okay? That we call it as BCC, FCC, these are all struts. We call it as a like that. And the other type is 2D lattices. 2D lattice means the cross section is same, that we will see. And the other type is TPMS. The good thing about the TPMS means it is of the easily printable structures, and the properties are higher for the TPMS structure. That is why if you find, I mean, as a researcher, if you know about it or not, if you find any journals or something, mainly people are working on the TPMS structure, because everyone well known that TPMS lattice structures have the better properties than the strut based. But it depends on the application also. If your application is like a strut based lattice, then you need to work on the strut based lattices. So, okay. So here I will show you the like strut based and few strut based lattices and this one, okay. So graph unit cell, see I told you, right, the first method, double press on it, you will see the available options, okay. So double press on it, you will see the available options. So I will take this first one, graph unit cell, this one. So it is asking the unit cell, again empty, ribbon button is there, you can press the ribbon so that you will see the available unit cells here. These are all like graph unit cell, means line diagram, with line diagrams we can generate. Like strut means lines only, right? That line we are giving a cross section. Again 2D hexagon means that line only, right? Line we are defining a cross section, okay? Same thing. So we will see the which one we body centric cubic lattice we will see, okay? And how the body centric cubic lattice means, this is the lines I told you, right? Lines it is there, okay? And we can see the implicit view to get better understand. Thickness we can vary, okay? See, this is a body BCC, right? Agree, BCC, right? And FCC, how it will look? See, this is how FCC will look like, okay. All the faces are centered here, see. And simple cubic, FCC, BCC, these only we studied in the chemistry, right? And the other types are there, octet columns, diamond, these things are also there, that we can also explore, see. Why we are calling this diamond? This looks like a diamond, right? So we are calling this as the diamond structure, okay. And so that is how we can see, okay. And the thickness we need to give. Thickness means this strut I am varying here, right. So Acha, tell me, like in the 30 mm unit cell, I am keeping, sorry, 30 mm lattice size cube is there. I am keeping 10 mm, 10 mm, 10 mm by 10 mm by 10 mm unit cell. So how many unit cells are repeated there? Pattern, I mean pattern, you can say pattern. How many are repeating there? See, 30 is there, right? Each unit has 30 is there, each section I am dividing into 10 mm on each direction. One direction 3, then what about other directions? What about Z? There is not X, Y, you said 3 into 3, what about Z? Z direction is also repeating, right? Like say, take a Rubik's cube only. Rubik's cube in a 3 by 3 by 3 by 3 is there, right? Each cube has a that one, right? So 3 into 3 into 3, 27, right? So that is all, okay. So the thickness we are adding, and the porosity, I will tell you the meaning of the porosity, we will see. Like I already told, we can reduce the weight rate, how we will see that we will see. So the thickness we can keep it as a 3 mm. Just see how the structure look. See, and we can change this into BCC, okay. See, this is a pattern, and each direction that one has a pattern. See, 3, 1, 2, 3, 3, 3. So 3 into 3 into 3, 27, right? 3 factorial. Sorry, 3 into 3 into 3, 27. Okay. Suppose the weight saving I will tell you how to do, then we can proceed. You just type it here, and remember that these are the in traditional design we might use like this, like we can go here and we can go here, right? But here only one thing we are using, I mean, as my personal experience, we are using it in the search option only. This is the search option. Like each option I don't know where it is. It may be some other tab. There are multiple tabs are there. In future the tabs may added also, but each option I cannot able to find where it is. So I will use I know the tab, so I can use it here. So weight I need to reduce, right? Weight, I mean how much weight is saved. So that we will see, okay. This is better. So weight saving. See, this is weight saving, right? See, as already told you, porous structure or lattice structure can reduce the weight, but we need to know how much it is reducing, and whether the strength is sufficient or not. That we can do for the analysis. That also we can do, okay. So here it is asking two types of bodies, comparison purpose. So how much it is reducing weight means how we can compare with original design. So I can compare, right? What is the original design here? The cube. How much is the size of the cube? 30 mm. So the original design is the cube, right? What is the name of the cube? Okay, I can rename this cube, as you said, cube 30 mm. Okay. Okay. So that cube has that original body has the name of cube 30 mm. Okay. So the original body I will type it here, cube 30 mm. Okay. It is giving, right? See. So I will press it. What is the light weighted body here? Light weighted body. I just say the name. You are able to see the name, right? BCC lattice structure, right? So that we can give a name then. Lattice underscore 0. Okay, I can give BCC or lattice 30 mm. Okay. Okay. So this I can press it, light weighted body, lattice 30 mm. Will calculate it. See, you are able to see, right? Okay. 64 mm we are 64, almost 64% we have reduced the weight. Okay, 64% we have reduced the 64% we have saved the material, means there is 36% material is remained there. Okay. So how I can further refine the how I can further reduce the weight of the structure, this cube? Take another one means? No, say whatever you want. I need the answer, whatever the answer, I don't mind actually. That is one example. Good. Like suppose because I told you that the geometry is not same for every structure. I told you in the video, right? BCC need not be similar to FCC. Suppose if I take FCC, that may be okay. We'll see that only. CC, right? How much? This is 64. See, 58 there means 42%. We are like material getting increasing, right? Because of the struts are adding more, right? So that is one type of method, like changing the structure. And the other type, the input parameters only you can see. 3 input parameters we are giving. One is like a structure, and other is like a unit cell size we are giving, and the third one is the thickness we are giving, right? So these 3 input parameters only we can play with the 3 input parameters, these 3 only. Okay. So what will happen? Now say the type of the structure completed, then the other type, then you can say thickness what, increase or decrease? Then what will happen? As you already quoted the first example, automobile, right? The sheet thickness we can reduce. Same thing. If we reduce the thickness, weight will increase, like weight will reduce, right? Means less amount of material will be there. That also we can try then. This is 58, right? So we can keep 2 mm. See, 78% we have reduced the weight. Okay. So that also proved, right? So what will happen then? What is the other method? What is the other input parameter is there? Size means what size? Unit cell size. Okay, what will happen? Unit cell size increase or decrease? Okay, if I decrease, what will happen? if you know the definition, then you will come to know that unit cell size 30 mm. Okay, I will tell you this. I will tell you this. Okay, wait. I will tell you this. In a 30 mm lattice, 10 by 10 by 10. I am repeating. So each direction has 3 unit cells. Suppose if I am keeping a 5 by 5 by 5, then how many unit cells I can get it? So there 27, right? 5 by 5 by 5. How many unit cells I will get it? No. In a 30 mm unit cell size. So 6 unit cells we are getting in each direction. 6 into 6 into 6, I think 216, right? Okay, I am poor in mathematics. 216, right? Okay. So 216 unit cells we are getting. So now tell me which is preferable, like 216, keeping the 216 unit cells, or means it is like the structure get compacted. The unit cell we are reducing, the unit cell size we are reducing. It means that the pattern is repeating more, right? So like if I am keeping a 10 mm unit cell this much of size, the unit cell size is increasing. It means pattern is very less, right? So what will happen if I increase the unit cell number of unit cells? What will happen if it is increasing? Number of unit cells we are increasing. That we will see. Okay, anyway, increase or decrease, that we will see now. That we will see then. Oh sorry, number of unit cells we are increasing. We are reducing the weight. Means the unit cell size I am decreasing. Okay. Suppose if I am taking 666 or 555. See, previously 78% we have ready, means only 22% material is remained. Now 37% weight reduced, means 63% material is there. So weight we are increasing. We are repeating the number of unit cells. See the structure, how dense the structure is. Okay, that is how we can calculate the structure. These 3 input parameters, like if you go through any research paper also, they will use these 3 input parameters. That is one type of structure, BCC. We will see other type of structure in some other design, not in design. Okay. So you know how to apply the lattice structure for a cube body, right? Now we will see we will take the advantage of the SolidWorks CAD designs. Okay, like there I will use the other type of structure. So I can take this other section. So first I will import the CAD model, right? I can't able to draw the CAD models here. I told you, right? First I will import the CAD models. Okay, there is option Control I to import. See here I already designed tensile specimen. I will use this. Okay, I will close this. Okay. See, the thing is, if you are applying a lattice body here, means in the entire body, means what will happen? We are keep fixing these things, means we are fixing in these things in the grippings. Even though we are keep fixing as a like as a mechanical engineer, we know that our main intention is on the gauge length, right? Gauge length, right? So we are applying the lattice on the gauge length only. Anyway, we are fixing those things in the lattice body, right? That grippers, so that we can keep it as a solid. Okay. So for that, what I did means I separated this into 3 bodies. And one more thing, entop is all about the Boolean operations only. We might have heard this term Boolean operation. Where we heard? There also. Then sets, like mathematics, in 10th class mathematics we might have heard the sets. Union operation, subtract operation, intersect operation. Union means combining. Subtracting means we are subtracting something from that body, original body. Intersecting means common body we are getting. What is the common need? Okay, that thing only. Entropy is all about the Boolean operations only. If you know about the Boolean union, subtract, intersection, then you can easily play with entropy, this software actually. Okay. So this one we are separating 3 bodies. Why we are separating these 3 bodies means our main intention is that we need to take this body only, apply the lattice structure. So we separated this in the 3 bodies in the SolidWorks software. Okay. You can also do here also, that I will do in the bone method. Why I can't able to use the SolidWorks software, I will tell. So I can convert this into, like if you want to perform any operation, further operation, once you imported, you need to convert that into implicit body, then only you can perform any operation. Okay, like be it a lattice or be it analysis or anything, you need to first convert into implicit body. So I will convert this into implicit body. So, first one I will convert this into implicit body, this I will rename it left, tensile left or other middle, this one is the middle, right. I will keep this as a middle and this one is the right. See previously, okay, I will show you one. What is the implicit body? I told you. Previously we are able to select the faces and lines, right, points, lines we are able to select it, right, but in implicit body we cannot able to select. I will show you that. See, I can't able to select, it is giving as the entire thing as a one body only, okay. We cannot able to select the lines or something, okay. In if you want to play anything in the faces or something, then you should have the, you should convert into that into CAD body, okay. Here my intention is that I need to apply the in the middle section, okay, lattice, this one I can apply later, okay, I will tell you that. So again same thing, lattice, rectangular lattice, I will drag this middle one, so my body is the middle one now, okay. And forgot to say, like on top can, you can see the compatible file formats here, these are the compatible file formats we can see. NTOP can accept the Parasolid, SolidWorks file format, NX format, Creo format, in future it may accept other formats also. So it can accept the step format also, okay. We call actually in general as a like mechanical or CAD designer, you need to know the like step file, we call it as a universal file format. Why we are calling this as the universal file format, any idea? Universal file format we can say like okay, any idea? Suppose I will tell you the example. You have designed some file like some glass water bottle or something, you have designed in the SolidWorks format, SolidWorks, okay, and your customer or your student may ask that they just want a viewing purpose. Editing purpose means you need that software only, but for the viewing purpose your customer may ask or your student or some other may ask. Your student may design and you have asked, but you don't have the SolidWorks software, you have some other software, Creo or something, because you might know that software, you have some other software, but you have designed a SolidWorks software, you have Creo software and you want to see the file, we cannot able to, so we need to ask the step or IGS format, so that the person can easily see the format, okay. Any software can accept the file format, that is why we call it universal, okay. So this type of file format is accepting, okay. So the middle volume is the middle body, okay, middle. So unit cell means in here previously we have kept the graph unit cell, right, now we will keep the TPMS unit cell, okay. Just double press on it, here you can see TPMS unit cell, wall TPMS unit cell, wall means it has a thickness, okay, shell type something, shell has a thickness, right. Again we can see xyroid, quartz, diamond, these things we can see, we can apply the xyroid, again the same thing, like you increase in the unit cell, increase in the thickness, everywhere the what is the happen to weight, that is same, okay. Can take 10 or 10 by 10 initially. So the thickness it is asking, I can take 2. So this is not a good, okay, we can take the 3, this thickness we can reduce 0.5, yeah, or otherwise 0.8. See we are getting like this, right. So this is the our lattice body and this is the left body, this is the right body, but the problem with this means these three are the separate bodies. Forget like yesterday some guy asked, if you want to do the analysis means I can't do, like during the analysis it will easily separate because the three are separate bodies. In terms of manufacturing also I will say, if you are exporting like this, you will print it with the separate bodies only. Again you need to stick with the Fevicol or something, that is the difficult, right. So we can stitch it here only using the Boolean operations, okay. So we need to combine these three bodies. Middle one is the lattice body, left body, right body. We need to combine these three bodies, right. So we will use the Boolean union, okay, Boolean union, okay. So we have three bodies, right. Here only two bodies are there. So press plus, and I will simply drag this one. And I forgot, like I told you, right, there is one more method, is the second method. how to identify which body I should place. The right thing to place in the right place, right? That is the one is important. You can see here the second one is the iconic method, okay. Icon means you can see here, icons is there, right? The same icon where it is there you can find it. The same icons are there here also, means that it is accepting those type of bodies, okay. See, icon is there, the same is there. So if I keep it here, it will place it easily, okay. And the thing is, all the implicit bodies are in the green color, all the lattice body in this color, and the imported cat bodies are in the yellow color. That is also recognition method, color recognition, color coding method, okay. So I can keep this one, okay. It will accept, drag this, and this is also implicit body. Once we are converted into, I told you right, implicit body, once we are converting into anything means that will be also implicit body. So this is also implicit body, I can keep this and write this one. Okay, now I combine. I will show you one more time, this one. Lattice, right, okay. See, here we have seen the gap, right, means that is not combined, there is a small tolerance gap is there. Suppose if I am pressing a I, and here you can see, we won't see a gap, that is a single body, right. So if I press this here, this is selecting as a single body. If I press here, this is selecting as a 3 different bodies, right. So this is how you can apply the thing, and you can explore the other lattices here also, gyroid or something you can explore here, okay. That is how you can fix it. This is the cat body, but what if there is a STL body, means STL means stereolithography, means tessellation, triangles is there, right, okay. So we will quickly wind up that bone or something, so that we can go for the break, okay. So I will take the other one. Okay, one example I will tell, which one I should take, brake pedal or bone. Okay. No, brake pedal means again cat body only, bone means STL body. Cat body we have already explored, right, the same thing. So bone I can take, okay. Same thing, bone means in between this is the bone, right, in between I am applying a lattice, but there is no faces there to select that portion. Here we can easily select the faces, right. So I can take this, okay. See, this is a meshed file, you can see here. See, as I told you, right, STL is all about the tessellation, triangles. You cannot able to find any square type of something. This is all about triangles only. First we will convert this into mesh body into implicit body, then only we can play anything, okay. So convert here, type implicit or something. We can see here, this is not implicit body from there, this is from implicit body from mesh. From mesh only we are getting implicit. So I will take that. I can see, you can see the icon again. I told you, right, icons. So this type of icon we can find it here, okay. I can keep this here, okay. See, this is converting. Now the real problem is that previously we have separated 2 body in the CAD geometry, right, like the middle portion, these things. But here the problem is the bone is the scanned one, means STL file. So we cannot able to select the faces. We need to use the Boolean operations here, okay. So this is your bone. I want to cut it from here. In this portion I want to apply the lattice. So I will cut that bone. So I will use the Boolean subtract. First I will cut it, right. Boolean subtract. The primary body is this one. Primary body means in this body only we are applying, okay. Boolean subtract, I am subtracting with respect to planes. The like plane, reference planes is there, right. With respect to reference planes I am taking, okay. So I need to separate this body, I need to extract the middle body. So how many cuts I should give? Extract the middle body? 2 cuts. Here 1 cut, here 1 cut, right. So 2 planes I need, right. Okay. So I will press this, so I can get the 2 planes. I can press plane or reference plane. I can use the plane from normal. See, your plane is here now, okay. You can change the view. Your plane is here. I will drag this here to in our required place. Here I want to drag, and this position you don't need, because reference plane is the infinite geometry. That is a like a reference geometry. that doesn't have dimensions. Okay. So okay, one more plane I will take, copy this, and I will use the same thing, like I will change the position here. It already cut. Okay. This is the body, right? Okay. This is the plane. This is the plane, second plane. Okay. So this is the portion. Okay, just to see the identify, we can put it here. So in this middle portion I need to get it. Okay. This middle portion I need to get. Suppose we will see whether cutting is correct process or not, we will see. See, we are getting this one, means we need to change the plane direction, then we can get the correct one. So 0 0 1 is there, right? This one we can change. This I can press -1. Both are in the same direction. This here in this direction you can see. So I will keep -1. Let's see. Okay, this I will keep +1 and this I will keep -1. Yeah, I am getting this one, right? So my intention is to apply the lattice on this body again. Yeah, one more thing, like what about the other two portions? We need to combine later, right? The other two portions also we need to get it right. So we need to, which operation we need? Boolean union is there. Union means combine. We already did the subtraction. Then which operation? There is one more operation, Boolean intersect. Common body we need to extract, right? That we will extract it. Okay. So Boolean intersect we can extract. So the original body is the bone one. Okay, this one, bone. Okay, I will rename it bone. Middle, this is this I can keep it as a bone middle. Just for the future reference I kept that. So bone I will use. The common body it will identify. Bone middle. Okay. See, we are good. Sorry. Oh, sorry. We need to subtract it actually. The common body we need to subtract that body. Common body we are getting, right? So Boolean subtract we need to do. Subtract from the original body we need to subtract. The common body we are getting here. So this one I can keep it here, primary body. This middle one I can keep it here. Okay. So we are getting this one, right? This is our non-design space body. We don't want to apply the lattice here. So I can apply the lattice here, middle body. Okay. So bone middle I can keep. 2 minutes we can complete it. Okay. So unit cell set, wall TPMS unit cell I can keep, gyroid. Okay, distant diamond I can keep, and some 10 by 10 by 10 I can keep, and the approximate thickness 2 mm I can keep. See, we are getting this one, right? And if you want to see the sectional view, you can see the sectional view. Okay, how the structure is changing. Okay, how the property bone structure is changing. Okay, and we need to combine these two bodies, right? These are the separate bodies. So the combination of body, this thing. So we can union this one. Okay, this body, lattice body, and this body. Two bodies are there. So this is how we can get it. Again, we can convert this into STL body, but the processing time will get more. That's why I am not converting here. That STL body you can use it for manufacturing. That is how we can use the topology. And weight saving, last thing, this one, then we can bind up. Weight saving we will see. Lightweighted body means this one, right? Combined body, bone final. You can keep this as. Okay. So this one, lightweighted body, bone final. Okay. This I will delete. And the original body is this one, bone, or primary body, right? So bone we can keep. Okay. So how much weight is reducing means you can see. See, 13% weight we have reduced. with this design. And if you want to reduce further means you can change the parameters and all those things. Okay. Yeah, that's all about the N topology and how to generate the lattice structures and all those things. We took the quickly wind up the, we took the two examples. One is like a lattice tensile sample, bone sample, and now we are applying for the cube sample. And the main thing is that 2D sketches we cannot do. That sketches and everything we can do it in the SolidWorks, and we can use it for use the 3D models. Like if you have a 3D model, original 3D models is there, we can play with NTOP. Okay, we cannot able to design everything in the NTOP, like the chairs and everything, water bottles, that we cannot do. That all needed 2D sketches. Okay, so original bodies if we have, we can play with that. Okay, yeah, that's all about it. Thank you. Yeah, you can go for, we can have.
ఓకే వచ్చారు అందరు. Okay, we'll start the next session. Project, you can use this website. Okay, is it visible? Yeah. That if you go to that window, you can download that features. Okay, if you go down, you can get a demo. There is instructions also. You can live demos also there. How to do this? Whatever you learned, na? How we can model it? How you can import your CAD file, whatever it may be, modeling files. You can add Boolean programs and all. Entire procedure is there. You can use this website and you can download and you can perform whatever you can able to do. No, you need to use your institute credentials or your email credentials. You can get it that download. Okay. Yes, they will give a link to your email. Then with that link you can able to download. Okay, and even they will give license for 1 year also for research work, license also they will give. With that license you can perform whatever. Next session we are going to start about this numerical modeling, that is numerical simulation of our laser DED process and as well as PBF process. And some of my students have performed the work in this laser as well as PBF process. Okay, in this process, you know how laser DED performs as well as the powder bed performs. To melt our powder particle materials, powders either we are feeding this coaxial nozzle or we are feeding by your additional feeding mechanisms or by axial mechanisms. Whatever may be the feeding mechanisms, that will melt and deposit to form the beads. That beads is multiple layers like deposition is taking place to fabricate your components. Like 3-dimensional, whatever the structure we are defined, according to our path planning, it is going to be fabricated and all. Right? If you observe here, this is component, how heat accumulation is accumulating over the build of the layers. When you are depositing, keep on depositing, because each layer is going to solidify quickly, rapid solidification takes place, and then the next layer again we are adding, again heat accumulation is taking place. Because of this we are having either maybe thermal deformations or maybe peel off or maybe structural deformation, and also we are having lot of residual stresses, right? But in numerical, what we can able to analyze? Different microstructures also, that is another aspects. But in numerical, how much deformation is going to take place? How we can able to control the heat? That is what, by correlating our the laser power, scan speed, and as well as the powder feed rates. With respect to that, we can able to correlate how much the heat has to be supplied to melt the, to minimize the solidification and to control the solidifications. That will affect the minimize components or as well as delamination to minimize the residual stress also. Even if you are clamping at one end, and if you keep on developing a single layers, what will happen? It will overhang and it will deform in the another end. It will become like a concave like structures and all. Why this is happening? Because heat accumulation is another end is freely, it is not supported, it is freely supported. That is why the deformation, more amount of stresses are deforming and to deform the part and all. These things and all we can able to numerically model flowing, and as well as where the more amount of resources is going to cause. And even if you want to make multi materials, bimetallic materials, because some materials are not easy to join, because that may be thermal deformation, quotient of thermal expansion, because one material may not be soluble in another, how much percentage, that is also another issues. And also it may form some kind of intermetallic materials also. But all these things identify how much thermal stresses, Warm stresses are going to generate between joining of these two materials. And this technology is completely we are available with welding. Already numerical, so many deform 3 ANSYs, so many welding models are there. With that same kind of welding models, now they adapted in the ANSYs as well as ANSYS additive. We can use ANSYS additive, we can use COMSOL, or we can use Abacus. There are like this so many number of softwares are there. With that softwares we can do perform the, we have to perform like my one of my master student in the last year, he has performed this experiment. We wanted to fabricate like thin wall fabrications. As I showed you in the video, single layer, how solidification is taking place, and if I go for the multiple layers, how heat accumulation is taking place at the different locations. These things understand by numerically. This will give some the idea of in what range we need to choose the process condition. Directly we don't know how the melting is taking place, how your solidification is taking place, what is the melting aluminum or titanium or stainless steel. That window can be minimum modeling. That what will give an idea what process range I need to select the power or the scan speed and all. With that, if you see the in the numerical modeling, we have pre-processing, solver, and as well as post-processing. In the pre-processor, we will define, because in numerical modeling we need to define number of elements, how the elements birth and death we has to be taking place. All these things has to be. Solver, we are importing what kind of meshes, and as well as we need to define what is the solvers, and as well as we need to give the boundary conditions. What is the boundary conditions for that? Then we can able to understand post processing after what are the data we are going to get it from the simulation aspect. That is what we can do in the post processing aspects. If you see in the pre processing, this is what done in the ANSYS. With that we can able to define. Here we have defined with some kind of a simple 3-4 layers of modeling aspect in the ANSYS additive and all. With that we have created a model in our any kind of a CATIA or PRO here, and after that defining model we have used simulating solver, that is what ANSYS simulating solver, and we have given a governing equations, because here how conduction is taking place and convection is taking place, and these are all the these things we have defined, and also as well as we need to define material properties, the thermal properties, geometric models, and as well as material properties. Means we need to define what thermal conductivity of that materials, what is the density of that material, properties, what is the melting point and as well as boiling point of that materials, whether we can use stainless steel. For all those things we need to enter all the physical properties of that materials. That how with that we have fed all the process things, and we have defined all the material properties in our ANSYS things, and then we have given the conditions for our, what is the laser beam we are using, how much power, what is the travel speed, how much powder we are feeding, and what is the wall height, and what is the focus radius, that is what the laser, that things we have to feed into our system, then we can able to perform things. These are the results we are going to get it after post processing. That is pre-processing, solver, then post processing. With that we can able to define. If you see, these are all the data. If you see in this, what we are getting in this, we are getting temperatures was time. With respect to time, how your solidification is taking place. This is what the cooling curves means. If you see at 0 seconds, your temperature is 1500. It's actually a multiply by 10, 1500 degrees centigrade. That's what for the stainless steel we have tried, and within a 40 seconds. Means that is not zigzag like manner, it will come down in a slowly cooling rate. That is because in 40 seconds entire your 1500 to it will come down, that much rapid solidification is going to take place. That is what 10 power 4 to 10 power 5 Kelvin per second solidification is taking place in your DD process. These things we can able to analyze. That's what we have defined our substrate models, and as well as your first layer we need to define, because the element has to grow and it has to die. That is what we are defining. This is called element birth technique, birth and death technique, that we are defined, and we can able to solve these things. Even component also we can able to do those things. That how geometry we are importing, like that geometry we need to define, and we have to give the constant and material properties, and with these you can able to get temperature distribution at what locations with respect to the area or the substrate, how the temperature distribution is taking place. And with these we can able to get residual stresses at different locations, how your residual stresses are going to be defined. Those things you can able to get it from your modeling. If you see in this animation here, this is what the substrate, and next we are defining the first layer. Means you can able to define for each element how it is deposition and solving is taking place. With that, for the single layer we got the results of your temperature distribution, and as well as the stresses, how one measure stresses are generating in the fabricated parts. Multiple layers, or if you go for your different kind. If you see here in the first layer it was deposited, for the second layer, this is what that is how we are defining our deposition strategies or the scan paths and all. If you compare that, the first what single layer in the previous slide and in the second slide, how much temperature distribution and thermal deformation has taken place. In the first layer only we can accumulating this much more amount of heat in the left side. See, the two layers was deposited, how much deformation has taken place, as well as temperature distributions. This is what we can able to define, and we can able to do in our numerical modeling, and then we can able to compare with our respect to our physical demonstration of LDD experiment or the right. And if you see, this is what we have done for some multi-materials, because we are facing lot of issues. Is this because of only the precipitates or the, or also maybe because of the temperature distributions or coefficient of thermal expansions? There will be solubility issues also, but we have not taken care just to identify, is it only because of these things and all? How much stresses, how much temperature distribution is taking place. For that we have taken a substrate a titanium, then over we have deposited a stainless steel. Then we have come cooling curves with respect to this bimetallic materials, and then we also simulated how much temperature distribution residual stresses is going to taking place with respect to the deposition of the models and all. And then we have come across that at the interface between bimetallics, there are a lot of amount of heat is generating, and delamination is taking place between your fabrication of the multiple materials and all. These things we have correlated with your experimental data, and we have come across some kind of a solution what perform we need to do further to solve these kind of issues. We can control the substrate temperature, or we need to do any other kind of experiments. This is what we have performed with our laser DD experimentations with ANSYS additive solutions. And also one of my students also working with abacus to simulate your powder bed fusion aspects with respect to the aluminum and other materials. He will show how to use our abacus, your student version abacus, and if you have any license version you can also use that. Okay, and he will train you how to define the models, how you can able to import that models, and how we have to define this element birth techniques for single models or for the multiple layers. You can apply same, but only thing we need to have the high kind of systems, servers or as well as workstations are required to perform. Otherwise it will take even months together to perform the experimentations to numerical simulations and all. Okay. Okay.
Yeah, we will be having access for only for this student version based. For other things version, here there will be some restrictions that the total nodes within the I mean deposition should be less than 1000. If it is more than 1000, it will not be acceptable. So we just need to go for like the meshing size and everything will be somewhat higher size. Initially, when you can download it from the Dassault systems, that will be called as a website. In that, you need to mail the company for the information. They will give you the license that you can use it for your student version with your institute email ID. Then here we will be having different options for just to go for the simulation. If you just see the module, we can have the part initially just like to create the geometry of the part, whatever the bead or something like a multi-layer deposition, everything. And then in the property option, you need to give the what are the materials. If you have seen here, if you already defined the materials earlier, then it will be fine. Otherwise we can give it in a something like if it is a stainless steel, aluminum, according to depends on how you are working, where and what you are working on it. So from here, if you just go to the general options, it will having some density. Then give us some what will be the values and all. In the mechanical, you can see multiple options like elasticity, plasticity, and also the expansion, deformation, plasticity. And then when it comes to thermal conductivity, specific it and everything. So uh, once you define the materials, here you will be having a option. I mean, like further we can go into the in-depth, and then third option will be assembly. If you have it in a single layer, then it will be there is no need to go for the assembly. Then if it is a like a assembly for multiple adding the each 3 layers, 4 layers, whatever it may be, number of layers. How you are going to simulate, what are the conditions you are going to give and everything, like whether it is a statistical heat transfer, those type of conditions. So someone will be only focusing, I mean like abacus is accessible for everything. It will come to AM and normal statistical analysis and like what will be the stresses and the deformation during the deposition, then you can only concentrate on that. If you want to be see how the heat distribution will be happening, you can just go for the choose the option like a heat transfer. Then we have the interaction will comes in multiple layers, because we in a single layer we are not going to have any interaction between other element. And then load will be some like it will be the boundary conditions which you are going to give it, what how you are going to give the pressure and load equal distribution. Mesh, you have no size of the element will be getting reduced. And then job is visualization, sketch, everything will be related with the final output. So first we need to initially we need to create a file and have to save the data. Here we have the option called set directory. Like stores where you are going to store it. So I just want to I will create a one folder. Paste it here. So it will go to the directory. So whatever the data you are going to have it will be stored in that. See, it was already there. If you go to here, that abacus, the folder which we have saved it. So whatever that simulation you are going to perform, that will be going to store in that that same folder. Then first thing is like we are going to keep a part. First we need to create a geometry. We will first deposit one single bead. like we will see the statistical analysis, and then we can go for that. Here we have the first go to the option like create part. Here it automatically it will ask whether it is a 3D planar, deform, 2D planar and everything, and we are going to work on the extrusion. So we just want to extrude the part. Approximation size of the interface what you are going to want to be take. Like if it is a 20 mm, 200 mm, according to that you can get. Here we are not going to give any units for the modeling, but in ourselves we are going to assume that we are taking the length in meters and time in seconds and pressure in bars, pascals. That's what. So here I just want to go for something like a 200 mm length. So I will just go with the 2.2. If you just click on the continue, it will give you the interface regarding the part geometry. For that you can go for the whatever the options you want to go for, whether it is a line or circle and rectangular, anything. We are going to work on the rectangular. We are creating a part. Just click on this. Now either you can draw it here or something like you can give the options like the what is the coordinates for the x and y. So I just want to give 0.1 in which we are going to have a 0.2 200 mm length. So I just want to only have the 100 mm length. So comma 0.1, just click on enter, and then it will ask you the origin point that we are going to give it as a 0, 0. Then click on enter. So click on done. Then we are going to have it a extrusion for 500 mm length. The total length will be so 0.5 I will say. So this is what you are going to get, normal bead for you just want to see. So once we create the geometry, go to the option called property, in which you are going to give the materials as we have already discussed. This is we are working on the statistical distribution. Then we just want to go for the density. So anything you can give something like 8100. It will be in kg per mm cube. Then go to mechanical elasticity. We don't want to make it complicated, so we just go with the initial things. Elastic Young's modulus something like a 200 e power 9. If it comes to 200 gigapascal. Then Poisson's ratio we mostly consider 0.3. Then click on OK. So it will the property, I mean like we have provided the initial data. Then go to the section. We are going to create this part will as a section. So it will automatically give you the options. Go to the continue and then click on OK. But we need to assign the section to this part, that you are going to get it from here. Assign the section. It will ask you the whether the sketch which we are going to we already produced, that whether it will be or not. Then click on OK. If you just click on OK, it will turn into green. That means we have assigned the material for that respective geometry. If you want to edit the material, you can go to option here. Otherwise, if you want to create another material, it will comes to material 2 or something. We are not going to have it anything. We already created one material, that is fine. That's material which is of a solid and homogeneous, which we have already taken it. Then now we are going for assembly. But here in that case, just go with a normal part. Just click on OK, because we are having only one part. If it is a multiple, then we want to we need to focus. And go to step option. Here, which we are going to work on it is a statistical analysis. So just go to this, then create step. First thing, it will ask you the statistical or general or heat transfer, anything that explicit dynamics, depends on what you want to perform on your work. So here we are just taking care of only statistical. Then go to continue. It will ask options like what are the time period and incrementation, what is the different I mean like a number of steps and everything. So here if you just see LGOM, if you can see here NLGOM, that depends on like normally it will default it will take off in an option like choose an option like off. But the thing is like sometimes we have a overhangs which is of more than if it is a straight, then it will be we are going to keep the load in a perpendicular to the, this exact load, but sometimes it will deform in which some more into the lower edge will be in the inside and this one. In that case, if you keep it this load in a perpendicular, but it will not have it. In that case, we are going to give this option. I mean like the load should be in this perpendicular direction. In that case, that will go for the large simulations. That will help in if you click on option. I mean like if you choose this algom as an on, then it will help us in whatever the overhangs it will be there, it will automatically take. Then time period we are just going to have it a 1 for whatever the I mean like according to your things you just need to go for that. And initial for example like I just want to be having a 10 steps, then I want to differentiate what is the initial length and 0.1 and then maximum. These are the number of increments for the first deposition to end. We just want to be, it should be in a large number, we can go for that. Then give a something like a 1 lakh we are going to give it. In other options you can go for, just click on OK. It was already there, we have already defined. Then go to the create output field option. It will ask you to go for step 1. Here you want to choose on what you are going to focus, like whether it is a thermal or stresses and everything. Since we have already chosen as a statistical analysis, we just want to only concentrate on the deformation and stresses and everything. Otherwise if you already have, I mean like initial conditions what you have chosen, that if you select here the pre-selected defaults, if you can see this option, that will automatically choose the stresses here. If you can see displacement, stresses and everything. If you don't want to be, you want to give it an exact thing what you want to be, then you can choose other things. Here whatever the stresses, what stresses they have chosen, like stress components and invariants, not all, and then strain, you can see plastic strain magnitude and logarithmic strain components and displacement in this way. Just click on OK. If you say yeah, same thing, if you just want to edit it again, you can go for the output option. Then we just want to go for the interaction, but here we don't have any interaction, so go to the next option called load. Here we are going to give the boundary conditions. See it here, we just want to see mechanical category, we are working on mechanical, and this is a pressure, we want to give the pressure, that is in a Pascal. It will ask you on which surface, on which direction you want to provide the pressure. I will select one end so that other end will be automatically. Go to the just click on done. It will ask you the magnitude, how much you want to give or something like that. Approximately whatever the amount you can give. If you have an exact amount, then you can go for that. I will just give a E4 5 something. Click on OK. So if you can see here, the scroll button, if you move forward, then it will zoom out. If you scroll inward, then it will zoom in. That is okay. Sorry. Now we are going to give the create boundary condition, that we are just as a symmetry, the sample is in a symmetry. Then go to continue, then it will ask you on which side. We just want to be give it an opposite to which we have given the pressure. So I will choose this area and click on this, and here how you are going to give the load, whether it is an equally distributed or you want to be particularly in a single direction. Then normally we will go for the e-cast tree, that will be conditions in all the directions. Since we have chosen a symmetry, click on OK. It will give you the all pressure in this direction. Sorry. Now we have provided the boundary conditions, and then go to the option mesh. Here if you see the seed part instance, sorry, we are just see, we just want to give it in a single part, then it will automatically choose the number of if the more number of layers, it will automatically take the conditions which you have provided for single option in the seed zone. But here we just go for the option called part, then give the mesh. Here it will ask the global size. By default we will take it less because it is a limited version. Then click on apply. Okay, then here it will give you the mesh part. It will ask whether okay to mesh or not. Then we will say yes, so it automatically given the mesh. And if you want to verify how much nodes and elements, then if you see this option icon, you can on the top just click on this. It will ask you which option it should be mesh. If you see it here, number of nodes are 132, number of elements are 50. Okay, if you number of nodes and elements, particularly someone wants to keep the data in their papers and they would just want to give a number, what are the elements they have distributed, then in that case for regarding the details you can go to that option. We have provided the mesh. Now go to the, we are not going to go any optimization, we are just going with a job that we are going to give it, assigning the job, create a job that is nothing but we are giving this result. Just click on OK. Here if you see it here, job manager, in that here it will ask you to submit the data, whatever the property you have presented till now, it will ask you to submit the data. If you just submit, see it was running here. If you want to monitor, we already given it from the incremental from point 1 to 1. So how it was automatically we have it would take in 6 increment size, and equally it was take the number of time step and everything, and what are the time in within the seconds from. Then if you go to that option called results, see here we just wanted to be in counter how it was distributed here. U is a magnitude, that is a stress. If you want it to be if you can see that I mean like how the distribution is happening during this after the deposition. If you want to make it in for like the frame rate should be less, then go to the option like animation options, click OK, then it will slowly distribute it. and I mean in the while keeping it in the publications, we don't want all this data. In that case, just go to this viewport. Yeah, here we are going to have it in a viewport annotation options. Here it will ask you what are the data you want to keep, whether it is only tried or less than anything. We don't want all the extra data, so we will just remove it. Then click apply, so it will already removed. Then okay, and then go to this option. It will ask you, sorry, it should be of a it will get, click OK. Now this, just a minute. Here you can see the legend options, like if you don't want, mostly we will go scientific, whatever the format here, if you can see. Otherwise in engineer we will just apply. It will go to in engineering data, how you are going to define your data, and a number of decimals, like up to what you want to keep, and this font style, everything you can change. There you can save the image. Actually one option will be there. Yeah, here you can save the file. There is a print. It will ask you all ports. All ports are current viewport, and PNG, it will better, it will give you the option. Choose the option where you have saved it. Click OK. Then save. So it have taken that you can change. And animation also, you can go for that. Apply. It should be animate, run the animation during while saving the option. Sorry. So frames are less, so it is going very quickly. According to your data requirement, you can go for that, whether it is a stress magnitude or deformation and everything. So now see more number of layers. In the same way, you just need to give. Sorry, I have taken it. I'm just creating new folder. Uh, Multi-layer. Copy this location. Keep here. Just click OK. Then same way we are going to give the part. Go to the option. We already have the point size. Go for continue. Then click on enter, then go for 0, 0. Initial steps will be common. Okay. Same. Initial steps will be common. Then go to property. We just want to add a material, new one. Density, how much you 7800. Suppose. Go to elasticity. 250 gigapascal if you say. Sorry. Poisson's ratio will be 3. Then go to plastic. It will ask you the yield stress, how much they want to give. I can say 20 megapascal. E power 5. Now we don't want to involve the strain rate, so we will just say OK, 0. And here we have the data. If you click on this, it will ask you the temperature, like a will be the values at other temperatures. Depends on the on what temperature you're working on. Someone will go for 100, 200 room temperature and everything. Complicated, then just unchoose this option. Then we have the expansion a little bit. We can say 200 at least. Thermal conductivity, suppose 30 of 500. Then according to the data on which material you're working on, everything, you can go for that option. Just click on OK. We have assigned that property. Then I just say sections, same thing. I just say OK. Go to that option, choose this body, done. So if you can see, now main thing is like assembly. Yeah, now we are going to have the multiple layers, so we need to if you see this option, create instance, then whatever the part you have already created, it will create if you just click on OK, it was generated part 1. And one more time, suppose we are going to check for 3 options, I mean like 3 layers. Again we will click on this, and this will be dependent on each material, I mean like you have to choose the instance type should be on a dependent, because each layer will be dependent on an already deposited layer. In that case, one more time click OK. So here we have seen part 1 2, one more time, because 3 layers. That now in order to get all the things into together, you just choose the option like a translate instance. It will, if you can see here, the access origin point xyz, we will say it will ask the select the instance to translate. First point we will choose this, done. If this, then another layer going to be attached here, whatever the layer you are already created. Then click OK, select enter. So you can see 2 layers it was there, and then one more time we will say OK, and we choose this second layer. So other layer will be assembled on top of the second. Click on done, choose this point. Otherwise, if you know the exact coordinators, you can go for that. Then we have chosen this origin point, then click on again enter, just click OK. Sorry, something it got mistake. Just a minute. Okay, part 1 is not there. It is moving in opposite direction. Sorry, just a wait. Now we'll first create the instance part 1. Okay, suppose we're going to work on 2 layers at least. Now we want to see the interaction between these. We have created assembly, then go to the step option, go to initial, work on the heat transfer, go to the continue. This is a transient, and time period how much you want to give, something like I will give some random value. Incrementation it will automatically take from here to here, and 1 lakh suppose. Okay, and if you go to here, this one rename, we will choose it as a heat 1, like now. One more we will create that also same. In that how going to give a time period, how much time you need to go for seconds, that is I will just randomly give 40 thing. Click on OK. We have given the heating one and the cooling one. In the same way, one we have to create, and it will be saying a heating 2. Give the heat source, and we need to cool it down. Same thing we need to repeat. But the problem in that case, if you have a more number of layers, it's better to go for using some code, Python codes, or those things will be helpful for you. Just click OK, and one more thing we will create, that's we call it as a cooling 2. Continue 40. Just click on OK. So we have given that all the time periods for this. If you can see it here, these are propagated, and go to the edit option. Here we are going to give the option like which one we are working. Thermal option. So we are working, we're going to check the nodal temperature, heat flux vector, and reaction fluxes, whatever the things it will be. Just click OK. So we have given it. We have the interaction things. We don't know whether the whatever the layers if you're seeing here, it may have some gaps and all. So we yes. So whatever the temperature or heat distribution comes from here, it should be. If you can see here, we have since this is working on cells, just we will say this bottom layer we are removing because it should be having some gap so that we can choose the interfaces of those two. We will just say click on remove. So go to dismiss. Here if you can see, create portals and not this. If you can see, continue, it will ask you the on which region you want to choose the I mean like the interface between. This is the top layer. We want to be the bottom surface of the top layer and the top surface of the bottom layer. In that case, I will choose the option surface. I will just rotate. I will choose this surface. It was highlighted and then done. Choose because on the top surface of the bottom layer here, if you ask you to bottom one, this option surface, I have chosen this one. So it will ask you any constraints if you want to modify it. If you can click on OK, see the interaction between these two, that you can see in the full body. You have already taken. So interaction was created. Now we will go to load boundary conditions. In this case, we are going to give the since we are working on the heat transfer. I mean here we just need to go for the heating one. Go to continue. It will ask you on which surface. We will say this one. So that load will be all around the surfaces. So what is the magnitude? You can give it some 20 or 1 power e power 5, anything. In like we have given the loading conditions of heat convection in the form of convection. Here you going to create a boundary condition. Okay, not required. Go to this option, edit. We have given the flux. Just a minute. Interaction. Here if you can see, not this one, it will ask you to surface film condition. This will give you the heat condition 15 and temperature how much it will be. We are working on the in the load. What will happen is like, so we are going to give it. It again depends on the formula called Q equals to absorption coefficient and the laser power which divided by some rate of deposition and also the travel speed, scan speed. That all the values we should need to calculate according to the what will be, sorry. For example, I have chosen different conditions like a 200 watt and absorption coefficient as a hence, and the scan speed will be 1 meter per second. I have calculated the heat flux, and then so here we need to give the heat flux as a, if you calculate that, you will get option like point 14, whatever the travel speed and everything you are going to say. So click on this OK, and then do it for all the things. One more same repetition for heating 2 also. Choose the option and same value you are going to give it. Click OK. Now we have given the heat flux for both the things, heating 1 and heating 2. Now we have given the boundary conditions. Now we just need to mesh it. In this case, in assembly it won't take, but because of, in that case we just need to go for part. It will choose the single part, same thing like seed parts which we have given it. It will number of nodes, if it is greater than 1000 it won't work. So just choose the better default option which it was suggested for initial learning conditions. This is everything. If you have a licensed version, you can work on the more number of fine mesh. That's what you can say. Just click on OK. It was done, and we will see the C part. It was meshed. Meshing was completed for the single one. If you choose the assembly, then it was automatically it will take for again. We have the given size, and what is the element type you want to give it. If it is a transient and these things, we just want to give in the assign which type of mesh element. Here you can see it will automatically and by default it will give the 3D stress, but we want to work on heat transfer. Now we are working on, so just click on OK. So this element type will be done for both the things. Now we are going to give them a job, sorry, create a job, continue, go for this option, submit. It will ask you the heating one, cooling one, everything. Just go for OK. It will register it. Yeah, this is what you can see. Go to the thermal one. If you can see the bottom layer is how the temperature would go. So, and one more thing we forgot to give, that is a model change. The model change, like the first when the top layer is heating, I mean like a bottom layer is heating, top layer should will not be having any effect on that, but when the second it need to cool, and bottom will also have some effect on the like here. If you can see this, not this, here you can say model change, that will give you the heat I mean like we are going to like so as and it is a element birth and death in this way. Same thing we have given it is a, if you can say for the heating one, continue, it will ask you by default I mean like it will ask you the region option. I have chosen the bottom region, click on OK. We are deactivating in this step and we will reactivate further once. I will just say click OK. In the same heating 2, MC2, continue, it will ask the region, choose the option, done. Go to here, you can see the inputs we have given model MC1 and MC2. Here it was already for the bottom layer heating 1 is created, but doesn't have any effect on the top layer because only we are working on the bottom layer. So in that case, go to option here, deactivate it again, and here sorry, edit option, you will see we are going to reactivate this step here. So modified in the same way, this one also, edit option, we are reactivating it. We'll modify according to that. So this will not have any effect on further layers. Click OK. Now again go to that job option. We already have the data. Now we can see more increments because of the layers. It was running, wait. Frame rate will be slow, so it will take time. If you can see that is happening. Contour options, continuous, we will apply. Same viewpoint, what you want. If you have, go for the multiple depositions and a more number of layers. Okay, thank you.